Welcome guys to this all-in-one PyTorch video. This video takes all parts from my beginner PyTorch playlist and combines it into one single video. The course goes from 0 to intermediate level and teaches you all the fundamentals you have to know to be confident with this deep learning framework. I will leave timestamps for each section in the description and all code is available on GitHub. Now before we start, I'd like to thank our sponsor of this course, Tab9. Tab9 is an AI-powered auto-completion tool that integrates with your IDE and helps you to code faster. It supports all modern programming languages and detects which language you are working in. In fact, I've been using this tool myself for a while now, and I have to say I'm really impressed with this functionality. It's one of my favorite plugins for VS Code now, and it also integrates with other IDEs. It uses deep learning under the hood and was trained on code from millions of repositories on GitHub. And with this knowledge, the tool can make predictions for code completions and suggestions that help you to code faster, reduce mistakes, and even discover best coding practices. And I have to admit, this works really well and it helps me in my workflow. And one nice and important thing to mention is that your code is totally safe, so you have complete privacy because Tab9's local completion model runs on your machine without sending any of your code anywhere. And the best part is, it's free. Their basic plan is free forever with the option to upgrade if you want a more advanced model. So I encourage you to download it, test it for yourself and see if you like it. I will leave you a link in the description. And with that, let's get started. And if you enjoy the content, be sure to like and subscribe. Hi everybody, welcome to a new tutorial series. In this series, we are going to learn how to work with PyTorch. PyTorch is one of the most popular machine learning and deep learning frameworks. It's really fun to work with it and develop cool applications. So I hope you watch this series and learn all about the necessary basics for this framework. So in this first video, I show you how we install PyTorch. So let's start. And for this, we go to the official website, pytorch.org. Then click on Get Started. Then select the newest PyTorch build. So right now, this is version 1.3. Then select your operating system. So in my case, it's a Mac. Then select the package manager with which you want to install PyTorch. So I highly recommend to use Anaconda. And if you haven't installed Anaconda yet and don't know how to use it, then please watch my other tutorial about Anaconda. So I will put the link in the description below. And then select the newest Python version. So here I select Python 3.7. And unfortunately on the Mac you can only install the CPU version right now. But if you are on Linux or Windows and want to have GPU support, then you can also install or have to install the CUDA toolkit first. So the CUDA toolkit is a development environment for creating high-performance GPU-accelerated applications. For this, you need an NVIDIA GPU in your machine. And if you have that, then you can go to the website developer.nvidia.com/CUDA-downloads. And then we have to be careful because right now the newest supported CUDA version by PyTorch is CUDA 10.1. So we have to get this version. So right now the newest version is 10.2. So we have to go to legacy releases. Then select the newest CUDA toolkit 10.1. Then select your operating system, so for example Windows 10. Then download the installer and follow the instructions. And this will also check if your system is suitable for the CUDA toolkit. So if this is successful, then we can go back to the PyTorch site and copy this command. So in my case on the Mac, now I need this command. So let's copy this. And now let's open up a terminal. And first of all, we want to create a virtual environment with Conda in which we want to install all of our packages and install PyTorch. So let's create an environment. Let's say Conda create -n and now give it a name. So I call this PyTorch, simply PyTorch. And then also specify the Python version. So let's say Python equals 3.7 and then hit enter. Now this will create your virtual environment with Python 3.7. Let's hit enter again to proceed. And this will take a while. And now it's done. So now we can activate this environment with conda activate PyTorch. And now we are inside of this environment, and we can see this because here in the beginning we have PyTorch in parentheses. So this is the name of the environment. And now let's paste our installation command from the website. So this will install PyTorch and all the necessary packages. So this will also take a couple of seconds. Now again, let's hit enter to proceed. And now it's done. So now we have installed PyTorch, and we can verify that by starting Python inside this environment. So let's say or type Python and enter. And now we have Python running, and now we can import the torch module. So if the installation was not correct, and right now you would get a module not found error, but in this case it is correct. And now we can, for example, create a torch tensor. So let's say x equals torch.rand and of size 3. And now we want to print our tensor. So this also works. And now we can also check if CUDA is available. So we can say torch.cuda.is_available. So in my case, it says false, but if you've installed the CUDA toolkit and also the GPU supported PyTorch packages, then this should say true. So yeah, so now we have installed on a PyTorch and can get started working with it. So I hope you enjoyed this and see you in the next tutorial. Bye. Hi everybody, welcome to a new PyTorch tutorial. In this video we are going to learn how to work with tensors, so how we can create tensors and some basic operations that we need. We will also learn how to convert from NumPy arrays to PyTorch tensors and vice versa. So let's start. So in PyTorch everything is based on tensor operations. From NumPy you probably know arrays and vectors, and now in PyTorch everything is a tensor. So a tensor can have different dimensions, so it can be 1D, 2D, or even 3D, or have more dimensions. So let's create an empty tensor. So first of all, we import torch, of course. And then we say x equals torch.empty. And then we have to give it a size. So for example, if we just say 1, then this is like a scalar value. So let's print our tensor. So this will print an empty tensor. So the value is not initialized yet. And now we can change the size. So for example, if we say 3 here, then this is like a 1D vector with 3 elements. So now if we run this, we see 3 items in our tensor. And now we can also make it 2D. So for example, let's say the size is 2 by 3. So this is like a 2D matrix. So now run this. And of course we can put even more dimensions in it. So now it would be 3D. And now, for example, now it would be 4D, but now I don't print it anymore because it's hard to see the 4 dimensions. But yeah, this is how we can create an empty tensor. And we can also, for example, create a tensor with random values by saying torch.rand and then give it the size. So let's say 2 by 2. And let's print our tensor again. We can also, the same like in NumPy, we can say torch.zeros. So this will put all zeros in it, or we can say torch.ones. So this will put ones in all the items. Then we can also give it a specific data type. So first of all, we can have a look at the data type by saying x.dtype. So if we run this, then we see by default it's a float 32, but we can also give it the dtype parameter. And here we can say, for example, torch.int. So now it's all integers. Or we can say torch.double. Now it is doubles. Or we can also say, for example, float 16 just. Yeah. And now if you want to have a look at the size, we can do this by saying x.size. And this is a function, so we have to use parentheses. So this will print the size of it. And we can also construct a tensor from data. So for example, from a Python list. So for example, here we can say x equals torch.tensor. And then here we put a list with some elements. So let's say 2.5, 0.1, and then print our tensor. So this is also how we can create a tensor. And now let's talk about some basic operations that we can do. So let's create two tensors with random values of size 2 by 2. So x and y equals torch.rand 2 by 2. So let's print x and let's print y. And yeah, so now we can do simple addition, for example, by saying set equals x plus y. So, and now let's print our C. So this will do element-wise addition, so it will add up each of the entries. And we could also use set equals torch.add and then x and y. So this would do the same thing. Now we could also do an in-place addition. So for example, if we say y dot and then add underscore x and then print y. So this will modify our y and add all of the elements of x to our y. And by the way, in PyTorch, every function that has a trailing underscore will do an in-place operation. So this will modify the variable that it is applied on. So yeah, so next to addition, of course, we could also use subtraction. So we can say C equals x minus y, or this would be the same as C equals torch.sub x and y. Now if you print C, then we can see the element-wise subtraction. Then we can also do a multiplication of each element. So this would be torch.mul. And again, we can do everything in place by saying y.mul underscore x. So this would modify our y. And then we can also do element-wise division. So this would be torch.div. And yeah, so this is some basic operations that we can do with tensors. And then we can also do slicing operations like you are used to from NumPy arrays. So let's say we have a tensor of size, let's say 5 by 3. And let's print this first. And now or print x. And now, for example, we can simply, or we can get all rows but only one column. So let's use slicing. So we here use a colon for all the rows but only the column 0. So let's print the whole tensor and only this. So here we see we have only the first column but all the rows. Or we can just say, for example, let's use the row number 1 but all columns. So this would print the second row and all the columns. Then we can also just get one element, so the element at position 1, 1. So this would be this value. And by the way, right now it prints the tensor. And if we have a tensor with only one element, we can also say, we can call the dot item method. So this will get the actual value, but be careful, you can only use this if you have only one element in your tensor. So this will get the actual value. And yeah, now let's talk about reshaping a tensor. So let's say we have a tensor of size, let's say 4 by 4, and print our tensor. And now if we want to reshape it, then we can do this by saying, or by calling the view method. So we say y equals x.view and then give it a size. So let's say we only want one dimension now. So let's print y. So now it's only a 1D vector. And of course the number of elements must still be the same. So here we have 4 by 4. So in total it's also 16 values. And for example, if we don't want to put the dimension or the value in one dimension, and we can simply say -1 and then specify the other dimension, and PyTorch will automatically determine the right size for it. So now it must be a 2 by 8 tensor. So we can also print the size again to have a look at the size. So this is size 2 by 8, so it's correctly determined the size. If we put a -1 here. So yeah, this is how we can resize tensors. And now let's talk about converting from NumPy to a torch tensor and vice versa. So this is very easy. So first of all, let's import NumPy again, or import NumPy as NP. And I think I have to, oh no, it's already installed here. So let's create a tensor first. So A equals torch dot, and let's create a tensor with ones of size 5. So let's print our tensor. And now if we want to have a NumPy array, we can simply say B equals A dot NumPy and then print B. So now we have a NumPy array. So if we print the type of B, then this will see, and this will print that we have a NumPy ND array. So yeah, this is how we can create from a tensor to a NumPy array. But now we have to be careful, because if the tensor is on the CPU and not the GPU, then both objects will share the same memory location. So this means that if we change one, we will also change the other. So for example, if we print, or if we modify B or a in place by saying a dot add underscore. Remember, all the underscore functions will modify our variable in place, and add 1. So if we add 1 to each element, and now first let's have a look at our A tensor, and now let's also have a look at our B NumPy array, then we see that it also added +1 to each of the elements here because they both point to the same memory location. So be careful here. And yeah, if you want to do it the other way around, so if you have a NumPy array in the beginning, so let's say A equals NumPy ones of size 5, and then print A. And now you want to have a torch tensor from a NumPy array, then you can say B equals torch, and then from underscore NumPy, and then put the NumPy array. So now we have a tensor, and this will, yeah, by default this will put in the data type float64. Of course, you could also specify the data type here if you want a different data type. And now again, we have to be careful if we modify one. So if we modify, for example, the NumPy array by incrementing each element. So now print our NumPy array. So we see that it incremented each value. And if we print B, then we see that our tensor got modified too. So again, be careful here. Yeah, but this happens only if your tensor is on the GPU. And this is one thing that we haven't talked about yet, because you can also do the operations on the GPU, but only if this is available. So if you have also installed the CUDA toolkit, and you can check that by saying if torch.cuda.is available. And so in my case on the Mac it will, and this will return false. But for example, if you are on Windows and you have CUDA available, then you can specify your CUDA device by saying device equals torch dot device, and then say CUDA here. And then if you want to create a tensor on the GPU, you can do this by saying x equals torch dot once, and then for example give it the size, and then say device equals device. So this will create a tensor and put it on the GPU, or you can first create it, so simply by saying y equals torch dot once of size 5, and then you move it to your device, to your GPU, by saying y equals y dot to, and then device. So this will move it to the device. And now if we do an operation, for example, c equals x plus y, then this will be performed on the GPU and might be much faster. Yeah, but now you have to be careful, because now if we would call c.numpy, then this would return an error, because NumPy can only handle CPU tensors, so you cannot convert a GPU tensor back to NumPy. So then again we would have to move it back to the CPU. So we can do this by saying c equals c dot to, and then as a string CPU. So now it would be on the CPU again. So yeah, this is all the basic operations that I wanted to show you. And one more thing, a lot of times when a tensor is created, for example, torch dot ones of size 5, then a lot of times you see the argument requires grad equals true. So by default this is false. And now if we print this, then we will also see here in our tensor that it will print requires grad equals true. So a lot of times in code you will see this, and this will tell PyTorch that it will need to calculate the gradients for this tensor later in your optimization steps. So whenever this means that whenever you have a variable in your model that you want to optimize, then you need the gradients. So you need to specify requires grad equals true. But yeah, we will talk about this more in the next tutorial. So I hope you enjoyed this tutorial, and if you liked it, please subscribe to the channel and see you next time. Bye. Hi everybody, welcome to a new PyTorch tutorial. Today we learn about the Autograd package in PyTorch and how we can calculate gradients with it. Gradients are essential for our model optimization, so this is a very important concept that we should understand. Luckily, PyTorch provides the Autograd package, which can do all the computations for us. We just have to know how to use it. So let's start to see how we can calculate gradients in PyTorch. So first of all, we import torch, of course. And now let's create a tensor x equals torch.randn of size 3. And now let's print our x. So this is a tensor with 3 values, so 3 random values. And now let's say later we want to calculate the gradients of some function with respect to x. Then what we have to do is we must specify the argument requires grad equals true. So by default this is false. And now if we run this again, then we see that also PyTorch tracks that it requires the gradient. And now whenever we do operations with this tensor, PyTorch will create a so-called computational graph for us. So now let's say we do the operation x plus 2 and we store this in an output. So we say y equals x plus 2. Then this will create the computational graph. And this looks like this. So for each node, we have or for each operation, we have a node with inputs and an output. So here the operation is the plus, so an addition. And our inputs are x and 2, and the output is y. And now with this graph and the technique that is called backpropagation, we can then calculate the gradients. I will explain the concept of backpropagation in detail in the next video, but for now it's fine to just know that how we can use it. So first we do a forward pass. So here we apply this operation, and in the forward pass we calculate the output y. And since we specified that it requires the gradient, PyTorch will then automatically create and store a function for us. And this function is then used in the backpropagation to get the gradients. So here y has an attribute grad underscore fn. So this will point to a gradient function, and in this case it's called add backward. And with this function we can then calculate the gradients in the so-called backward pass. So this will calculate the gradient of y with respect to x in this case. So now if we print y, then we will see exactly this grad fn attribute. And here this is an add backward function. So because here our operation was a plus, and then our then we do the backpropagation later, so that's why it's called add backward. And let's do some more operation with our tensors. So let's say we have c equals y times 2, for example. So this tensor then also has this grad function attribute. So here grad fn equals mul backward, because here our operation is a multiplication. And for example, we can say c equals c dot mean. So we can apply a mean operation. And then our gradient function is the mean backward. And now when we want to calculate the gradients, the only thing that we must do is to call c dot backward. So this will then calculate the gradient of c with respect to x. So x then has a gradient, a dot grad attribute where the gradients are stored. So we can print this. And now if we run this, then we see that we have the gradients here in this tensor. So this is all we have to do. And now let's have a look what happens when we don't specify this argument. So first of all, if we print our tensors, then we see that they don't have this grad function attribute. And if we try to call the backward function, then this will produce an error. So it says tensors does not require grad and does not have the grad function. So remember that we must specify this argument and then it will work. And one thing that we should also know is, so in the background, what this basically does, this will create a so-called vector Jacobian product to get the gradients. So this will look like this. I will not go into the mathematical details, but we should know that we have the Jacobian matrix with the partial derivatives, and then we multiply this with a gradient vector, and then we will get the final gradients that we are interested in. So this is also called the chain rule, and I will also explain this more in detail in the next video. But yeah, we should know that actually we must multiply it with a vector. So in this case, since our c is a scalar value, we don't have to put the don't have to use an argument here for our backward function. So our c here has only one value, so this is fine. But let's say we didn't apply the mean operation. So now our c has more than one value in it. So it's also of size 1 by 3. And now when we try to call the backward function like this, then this will produce an error. So grad can be implicitly created only for scalar outputs. So in this case, we have to give it the gradient argument. So we have to create a vector of the same size. So let's say v equals torch.tensor. And here we put, for example, 0.1, 1.0, and 0.001. And we give it a data type of torch.float32. And then we must pass this vector to our backward function. And now it will work again. So now if we run this, then this is okay. So we should know that in the background, this is a vector Jacobian product. And a lot of times the last operation is some operation that will create a scalar value. So it's okay to call it like this without an argument. But if this is not a scalar, then we must give it the vector. And yeah, then some other thing that we should know is how we can prevent PyTorch from tracking the history and calculating this grad fn attribute. So for example, sometimes during our training loop, when we want to update our weights, then this operation should not be part of the gradient computation. So in one of the next tutorials, I will give a concrete example of how we apply this Autograd package, and then it will become clearer maybe. But yeah, for now we should know how we can prevent this from tracking the gradients, and we have three options for this. So the first one is to call the requires grad underscore function and set this to false. The second option is to call x.detach. So this will create a new tensor that doesn't require the gradient. And the second option would be to wrap this in a with statement. So with torch dot no grad. And then we can do our operations. So yeah, let's try each of these. So first we can say x dot requires grad underscore and set this to false. So whenever a function has a trailing underscore in PyTorch, then this means that it will modify our variable in place. So now if we print x, then we will see that it doesn't have this require grad attribute anymore. So now this is false. So this is the first option. And the second option would be to call x detach. So we say y equals x.detach. So this will create a new vector with the same, or a new tensor with the same values, but it doesn't require the gradient. So here we see that our y has the same values but doesn't require the gradients. And the last option is to wrap it in a torch, in a with statement, with torch.noGrad. And then we can do some operations. For example, y equals x plus 2. And now if we print our y, then we see that it doesn't have the gradient function attribute here. So yeah, if we don't use this and would run it like this, then our y has the gradient function. So these are the three ways how we can stop PyTorch from creating this gradient functions and tracking the history in our computational graph. And now one more very important thing that we should also know is that whenever we call the backward function, then the gradient for this tensor will be accumulated into the .grad attribute. So the values will be summed up. So here we must be very careful. So let's create some dummy training example where we have some weights. So this is a tensor with ones in it of size, let's say 4, and they require the gradient, so requires grad equals true. And now let's say we have a training loop where we say for epoch in range, and first let's only do one iteration, and here we do, let's say, model output equals, let's say, weights times 3.sum. So this is just a dummy operation which will simulate some model output. And then we want to calculate the gradients. So we say model output dot backward. And now we have the gradient. So we can call weights dot grad and print this. So our gradients here are 3. So the tensor is filled with 3s. And now if we do another iteration, so if we say we have 2 iterations, then the second backward call will again accumulate the values and write them into the grad attribute. So now our grad has 6s in it. And now if we do a third iteration, then it has 9s in it. So all the values are summed up, and now our weights or our gradients are clearly incorrect. So before we do the next iteration and optimization step, we must empty the gradients. So we must call weights.grad.zero underscore. And now if we run this, then our gradients are correct again. So this is one very important thing that we must note during our training steps. And later we will work with the PyTorch built-in optimizers. So let's say we have a optimizer from the Torch optimization package. So torch.optim.sgd for stochastic gradient descent, which has our weights as parameters and some learning rate. And now with this optimizer, we can call or do a optimization step. And then before we do the next iteration, we must call the optimizer.zero grad function, which will do exactly the same. So yeah, we will talk about the optimizers in some later tutorials, but yeah, for now, the things you should remember is that whenever we want to calculate the gradients, we must specify the requires grad parameter and set this to true. Then we can simply calculate the gradients with calling the backward function. And before we want to do the next operation or the next iteration in our optimization steps, we must empty our gradient. So we must call the zero function again. And we also should know how we can prevent some operations from being tracked in the computational graph. And that's all I wanted to show you for now with the Autograd package. And I hope you liked it. Please subscribe to the channel and see you next time. Bye. Hi everybody, welcome to a new PyTorch tutorial. In this video I'm going to explain the famous backpropagation algorithm and how we can calculate gradients with it. I explain the necessary concepts of this technique and then I will walk you through a concrete example with some numbers. And at the end we will then see how easy it is to apply backpropagation in PyTorch. So let's start. And the first concept we must know is the chain rule. So let's say we have two operations or two functions. So first we have the input x and then we apply a function a and get an output y. And then we use this output as the input for our second function. So the second function b. And then we get the final output c. And now we want to minimize our c. So we want to know the derivative of c with respect to our x here in the beginning. And we can do this using the so-called chain rule. So for this, we first compute the derivative of c with respect to y and multiply this with the derivative of y with respect to x. And then we get the final derivative we want. So first here, we compute the derivative at this position. So the derivative of this output with respect to this input. And then here, the derivative of this output with respect to this input. And then we multiply them together and get the final gradient we are interested in. So that's the chain rule. And now the next concept is the so-called computational graph. So for every operation we do with our tensors, PyTorch will create a graph for us. So where at each node we apply one operation or one function with some inputs and then get an output. So here at this case, in this example, we use a multiplication operation. So we multiply x and y and then get c. And now at these nodes, we can calculate so-called local gradients, and we can use them later in the chain rule to get the final gradient. So here, the local gradients, we can compute two gradients, the gradient of c with respect to x, And this is simple since we know this function here. So this is the gradient of x times y with respect to x, which is y. And here in the bottom, we compute the derivative of x times y with respect to y, which is x. So local gradients are easy because we know this function. And why do we want them? Because typically our graph has more operations, and at the very end we calculate a loss function that we want to minimize. So we have to calculate the gradient of this loss with respect to our parameter x in the beginning. And now let's suppose at this position we already know the derivative of the loss with respect to our c, and then we can get the final gradient we want, so that with the chain rule, so the gradient of the loss with respect to x is then the gradient of loss with respect to c times our local gradient, so the derivative of c with respect to x. And yeah, this is how we get the final gradient then. And now the whole concept consists of 3 steps. So first we do a forward pass where we apply all the functions and compute the loss. Then at each node we calculate the local gradients. And then we do a so-called backward pass where we compute the gradient of the loss with respect to our weights or parameters using the chain rule. So these are the 3 steps we are gonna do. And now we look at a concrete example. So here we want to use linear regression. And if you don't know how this works, then I highly recommend my machine learning from scratch tutorial about linear regression. I will put the link in the description. So basically we model our output with a linear combination of some weights and an input. So our y hat or y predicted is w times x. And then we formulate some loss function. So in this case, this is the squared error. Actually, it should be the mean squared error, but for simplicity, we just use the squared error. Otherwise, we would have another operation to get the mean. So the loss is the difference of the predicted y minus the actual y, and then we square it. And now we want to minimize our loss. So we want to know the derivative of the loss with respect to our weights. And how do we get that? So we apply our 3 steps. First, we do a forward pass and put in the x and the w. And then here we put in the y and apply our functions here. And then we get the loss. Then we calculate the local gradients at each node. So here, the gradient of the loss with respect to our s. Then here the gradient of the s with respect to our y hat. And here at this node the gradient of y hat with respect to our w. And then we do a backward pass. So we start at the end. And here we have first we have the derivative of the loss with respect to our s. And then we use them, and we also use the chain rule to get the derivative of the loss with respect to the y hat. And then again we use this and the chain rule to get the final gradient of the loss with respect to our w. So let's do this with some concrete numbers. So let's say we have x and y is given. So x is 1 and y is 2 in the beginning. And so these are our training samples, and we initialize our weights. So let's say, for example, we say our w is 1 in the beginning. And then we do the forward pass. So here at the first node, we multiply x and w. So we get y hat equals 1. Then at the next node, we do a subtraction. So y hat minus y is 1 minus 2 equals minus 1. And at the very end, so we square our s, so we have s squared. So our loss then is 1. And now we calculate the local gradient. So at the last node, we have the gradient of the loss with respect to s. And this is simple because we know the function. So this is the gradient of s squared. So this is just 2s. And then at the next node, we have the gradient of s with respect to y hat, which is the gradient of the function y hat minus y with respect to y hat, which is just 1. And then here at the last node, we have the derivative of y hat with respect to w. So this is the derivative of w times x with respect to w, which is x. And also notice that we don't need to know the derivatives in this graph lines. So we don't need to know what is the derivative of s with respect to y. And also here we don't need this because our x and our y are fixed. So we are only interested in our parameters that we want to update here. And yeah, and then we do the backward pass. So first, now we use our local gradients. So we want to compute the derivative of the loss with respect to y hat. And here we use the chain rule with our two local gradients that we just computed, which is 2s times 1 and s is minus 1, which we calculated up here. And then so this is minus 2. And now we use this derivative and also this local gradient to then get the final gradient, the gradient of the loss with respect to our w, which is the gradient of the loss with respect to y hat, times the gradient of y hat with respect to w, which is minus 2 times x, and x is 1. So the final gradient is minus 2. So this is the final gradient then that we want to know. And yeah, that's all how backpropagation works. And let's jump over to our code and verify that PyTorch get these exact numbers. So let's remember x is 1, y is 2, and w is 1. And then our first gradient should be minus 2. So let's see how we can use this in PyTorch. And first of all, we import torch, of course. Then we create our vector, our tensor. So we say x equals torch.tensor, and this is 1. And then our y equals torch.tensor with 2. And then our initial weight is a tensor also with 1. So 1.0 to make it a float. And here with our weight, we are interested in the gradient. So we need to specify requires grad equals true. And then we do the forward pass and compute the loss. So we simply say y hat equals w times x, which is our function. And then we say loss equals y hat minus the actual y. And then we square this. So we say this to the power of 2. And now let's print our loss and see this is 1 in the beginning. And now we want to do the backward pass. So let's do the backward pass, and PyTorch will compute the local gradients automatically for us and also computes the backward pass automatically for us. So the only thing that we have to call is say loss backward. So this is the whole gradient computation. And now our w has this .grad attribute, and we can print this. And now this is the first gradient after the first forward and backward pass. And remember, this should be -2 in the beginning. And here we see we have a tensor with -2. So this is working. And the next steps would be, for example, now we update our weights and then we do the next forward and backward pass and do this for a couple of iterations. And yeah, that's how backpropagation works and also how easy it is to use it in PyTorch. And I hope you enjoyed this tutorial. Please subscribe to the channel and see you next time. Bye. Hi everybody, welcome to a new PyTorch tutorial. In this tutorial I show you a concrete example of how we optimize our model with automatic gradient computation using the PyTorch Autograd package. So we start by implementing the linear regression algorithm from scratch, where we do every step manually. So we implement the equations to calculate the model prediction and the loss function. Then we do a numerical computation of the gradients and implement the formula. And then we implement the gradient descent algorithm to optimize our parameters. When this is working, we see how we can replace the manually computed gradients with the automatic backpropagation algorithm from PyTorch. So this is step number 2. And in the third step, we replace the manually computed loss and parameter updates by using the loss and optimizer classes in PyTorch. And in the final step, we replace the manually computed model prediction by implementing a PyTorch model. So when we understood each of these steps, PyTorch can do most of the work for us. Of course, we still have to design our model and have to know which loss and optimizer we should use, but we don't have to worry about the underlying algorithms anymore. So now this video will cover steps 1 and 2. And in the next video, we will see the steps 3 and 4. So let's start. And I assume that you already know how linear regression and gradient descent works. And if not, then please watch my machine learning from scratch tutorial about this algorithm, because now I will not explain all the steps in detail, but I put the link in the description. So now we do everything from scratch. So we use only NumPy, so we import NumPy as NP, and then we use linear regression, so we use a function which just does a linear combination of some weights and our inputs, and we don't care about the bias here. So in our example, let's say f equals 2 times x, so our weight must be 2. And then let's do some training samples. So let's say x equals numpy.array. And then we put some training samples. So let's say 1, 2, 3, and 4. And this will be of NumPy, or let's give this a data type and say this is numpy.float 32, and then we also want a y, and since our formula is 2x, we have to multiply each of the values by 2, so 2, 4, 6, and 8. And now we initialize our weights, so we simply say w equals 0 in the beginning, and now we have to calculate our model prediction, and we also have to calculate the loss, and then we have to calculate the gradient. So now we do each of these steps manually. So let's define a function and we call this forward. So this is a forward pass to follow the conventions of PyTorch, which will get x, and then our model output is simply w times x. So this is the forward pass. Now the loss. So here we define the function loss, which depends on y and y predicted. So this is the model output. And now here in this case, this is the loss equals the mean squared error in the case of linear regression. And we can calculate this by saying this is, let's say, y predicted minus y, and then to the power of 2, and then we do the mean operation. So this is the loss, and now we manually have to calculate the gradient of the loss with respect to our parameters. So let's have a look at the mean squared error. So the formula is 1 over n, because it's the mean. And then we have our w times x, so our prediction minus the actual value to the power of 2. And now if you want to have the derivative, so the derivative of this, let's call this j, or objective function, with respect to w equals 1 over n. And then we have 2 times x, and then times w times x minus y. So this is the numerical computed derivative. So please double check the math for yourself. And now we implement this. So we say define gradient, which is dependent on x and y, and also y predicted. And now we can do this in one line. So we return NumPy dot. We need a dot product of 2 times x. And then here we have y predicted minus y. So this is this formula here. And then, of course, we also need the mean. So let's say this is dot mean. We can simply do it like this in NumPy. And now, yeah, these are the things we need. Now let's print our prediction before the training. So let's print, and we use an f string. So prediction before training. And let's say we want to predict the value 5, which should be 10. And here we can do, in the f string, we can actually use an expression. So we can call this forward method, and with 5. And let's say we only want 3 decimal values. And now let's start our training. So let's define some parameters. So we need a learning rate, which is, let's say, 0.01. And then we need a number of iterations. So we say n iters equals 10. And now let's do our training loop. So we say for epoch in range n iters. And then first we do the prediction, which is the forward pass. So this is the forward pass. And we can simply do this with our functions. So we say y prediction, or y pred equals forward. And then we put in our capital X. And now we want to have the loss. So our loss L equals the loss of the actual y and our y predicted. Now we need to get the gradients. So our gradients with respect to w, so dw equals the gradient function that we just implemented, which is dependent on x and y and the y predicted. Y pred. And now we have to update our weights. And yeah, so the update formula in the gradient descent algorithm is just we go into the negative direction of the training of the gradient, so minus x, and then here the step width, or the so-called learning rate, times our gradient. So this is the update formula. And then let's say we also want to print some information here. So we say if epoch modulo, just say 1 here, because now we want to print every step. If this is 0, we want to print, let's say we want to print the epoch, and here we print epoch plus 1. And then we want to get the weight, which is the weight W, also just 3 decimal numbers. And then we also want to have the loss. So the loss equals the loss, and here we say 0.8, let's say. And yeah, and then at the end we want to print the prediction after the training. So now let's print prediction after training. And yeah, so now let's run this and see what happens. So everything should be working. And now, so yeah, before our training, the prediction is 0. And then for each step, remember that our formula should be 2 times x. So our W should be 2 in the beginning. And we see that with each training step, it increases our weights and it decreases our loss. So it gets better with every step. And after the training, our model prediction is 9.999. So it's almost there. So let's say, for example, now we want to have more iterations. Here, say we only did 10 iterations, which is not much. Now if we run this and let's print every second step only, then we see in the end our loss is 0 and the prediction is correct. Now this is the implementation where we did everything manually, and now let's replace the gradient calculation. So let's select all of this and copy this into a separate file. And now we don't use NumPy anymore. So now let's only import Torch and do everything with PyTorch. And of course, what we now want to get rid of is this gradient, the manually computed gradients. So we simply delete this. We don't need this anymore. And now we don't have NumPy arrays. So this is now a torch.tensor. And our data type is now a torch.float32, and the same with our y, which is now a torch.tensor, and also the data type is from the torch module, but everything else is the same here, so the same syntax. And now our w also has to be a tensor. So let's say this is a torch.tensor with 0.0 in the beginning, and it also gets a data type of, say, torch.float32. And since we are interested in the gradient of our loss with respect to this parameter, we need to specify that this requires the gradient computation, so requires grad equals true. Now the forward function and the loss function is still the same because we can use the same syntax in PyTorch. And now in our training loop, the forward pass is still the same, the loss is the same. And now the gradient, this is the equal to the backward pass. So remember, in backpropagation, we first do a forward pass. That's why we use this syntax. And then later for the gradients, we use the backward pass. So here we simply call L.backward. And this will calculate the gradient of our loss with respect to W. So PyTorch does all the computations for us. And now we update our weights, but here we want to be careful. And I explained this in the tutorial about the Autograd package, because we don't want to be, this operation should not be part of our gradient tracking graph. So this should not be part of the computational graph. So we need to wrap this in a with torch dot no grad statement. And then one more thing that we should also know, and I also talked about this already, we must empty or zero the gradients again, because whenever we call backward, it will write our gradients and accumulate them in the w.grad attribute. So before the next iteration, we want to make sure that our gradients are 0 again. So we can say w times grad times 0 underscore. So this will modify it in place. And now we are done. And now let's run this and see if this is working. And w is not defined. Oh yeah, of course, this is now w.grad. And let's try this again. And now it's working. And now we also see that it will increase our w and it will decrease our loss. And here we said we had 20 iterations, but it's not correct, not completely correct. And this is because the backward or the backpropagation is not as exact as the numerical gradient computation. So let's try some more iterations here. Let's say we want 100 iterations and print our update every 10th step. So let's try this again. And now we see after the training is done, we have the correct prediction. So yeah, that's it for this video. And in the next video, we will continue here and replace the manually computed loss and weight updates with PyTorch loss and optimizer classes. So if you like this video, please subscribe to the channel and see you next time. Bye. Hi everybody, welcome back to a new PyTorch tutorial. In the last tutorial, we implemented logistic regression from scratch and then learned how we can use PyTorch to calculate the gradients for us with backpropagation. Now we will continue where we left off, and now we are going to replace the manually computed loss and parameter updates by using the loss and optimizer classes in PyTorch. And then we also replace the manually computed model prediction by implementing a PyTorch model. Then PyTorch can do the complete pipeline for us. So this video covers steps 3 and 4. And please watch the previous tutorial first to see the steps 1 and 2. So now let's start. And first I want to talk about the general training pipeline in PyTorch. So typically we have 3 steps. So the first step is to design our model. So we design the number of inputs and outputs. So input size and output size. And then also we design the forward pass with all the different operations or all the different layers. Then as a second step, we design or we come up with so we construct the loss and the optimizer. And then as a last step, we do our training loop. So this is the training loop. So we start by doing our forward pass. So here we compute, or let's write this down, compute the prediction. Then we do the backward pass. So we get the gradients, and PyTorch can do everything for us. We only have to define or to design our model. So, and after we have the gradients, we can then update our weights. So now we update our weights, and then we iterate this a couple of times until we are done. And that's the whole pipeline. So now let's continue, and now let's replace the loss and the optimization. So for this, we import the neural network module. So we import torch.nn as nn. So we can use some functions from this. And now we don't want to define the loss manually anymore. So we can simply delete this. And now down here, before our training, we still need to define our loss. So we can say loss equals, and here we can use a loss which is provided from PyTorch. So we can say nn.mse loss, which is exactly what we implemented before. So this is the mean squared error, and this is a callable function. And then we also want a optimizer from PyTorch. So we say optimizer equals torch.optim from the optimization module. And then here we use SGD, which stands for stochastic gradient descent, which will need some parameters that it should optimize, and it will need this as a list. So we put our W here. And then it also needs the LR, so the learning rate, which is our previously defined learning rate. And then in our training loop, so the loss computation is now still the same, because this is a callable function which gets the actual y and the predicted y. And then we don't need to manually update our weights anymore. So we can simply say optimizer.step, which will do an optimization step. And then we also still have to empty our gradients after the optimization step. So we can say optimizer.0grad. And now we are done with step 3. So let's run this to see if this is working. And so yeah, it's still working. Our prediction is good after the training. And let's continue with step 4 and replace our manually implemented forward method with a PyTorch model. So for this, we also don't need our weights anymore, because then our PyTorch model knows the parameters. So here we say model equals nn.linear. So usually we have to design this for ourselves, but since this is very trivial for linear regression, so this is only one layer, this is already provided in PyTorch. So this is nn.linear, and this needs an input size and an output size of our features. And for this we need to do some modification. So now our x and y need to have a different shape. So this must be a 2D array now, where the number of rows is the number of samples, and for each row we have the number of, or the features. So this has a new shape. A new shape that looks like this. And the same for our y. So our y is the same shape now. So 2, 4, 6, and 8. So now let's get the shape. So this is y. I have to be careful now. So we can say number of samples and number of features equals x dot shape. And now let's print this. So print the number of samples and the number of features. And now let's run this. So this will run into an error, but I think we get until here. So the shape is now 4 by 1. So we have 4 samples and 1 feature for each sample. And now we define our model. So this needs an input and an output size. So the input size equals the number of features, and the output size is still the same. So this is also the number of features. So this is 1 as an input size and 1 as an output size. Now we need to give this to our model. So we say here input size and output size. And then one more, then when we want to get the prediction, we can simply say, we can call the model, but now this cannot have a float value, so this must be a tensor. So let's create a test tensor. Let's say x test equals torch.tensor, which gets only 1 sample with 5, and then it gets a data type of, say, torch.float32, and then here we pass the test sample, and since this is only has only one value, we can call the dot item to get the actual float value then. So now let's copy and paste this down here. And now we also have to modify our optimizer here, so we don't have our weights now. So this list with the parameters, here we can simply say model.parameters and call this function. And now here for the prediction, we simply call the model. And now we are done. So now we are using the PyTorch model to get this. And also down here, now if we want to print them again, we have to unpack them. So let's say W and an optional bias equals model parameters. This will unpack them, and then if we want to print the actual, this will be a list of lists. So let's get the first, or the actual first weight with this, and we can also call the item because we don't want to see the tensor. And now I think we are done. So let's run this to see if this is working. And yeah, so the final output is not perfect. So this might be because the initialization now is randomly, and also this optimizer technique might be a little different. So you might want to play around with the learning rate and the number of iterations. But basically it works and it gets better and better with every step. And yeah, so this is how we can construct the whole training pipeline. And one more thing. So in this case, we didn't have to come up with the model for ourselves. So here we only had one layer, and this is already provided in PyTorch. But let's say we need a custom model. So let's write a custom linear regression model. Then we have to derive this from nn.module, and this will get a init method which has self and which gets the input dimensions and the output dimensions. And then here we call super, the super class, so super of linear regression with self and then dot init. This is how we call the super constructor. And here we would define our layers. So in this case, we say our self.lin, our linear layer, equals nn.linear. And this will get the input dimension and the output dimension. And then we store them here. And then we also have to implement the forward pass in our model class. So self and x. And here we can simply return self.linear of x. And this is the whole thing. And now we can say our model equals linear regression with the input size and the output size. And now this will do the same thing. So now this is just a dummy example because this is a simple wrapper that will do exactly the same. But basically this is how we design our PyTorch model. So now let's comment this out and use this class to see if this is working. And yeah, so it's still working. So that's all for now. And now PyTorch can do most of the work for us. Of course, we still have to design our model and have to know which loss and optimizer we want to use. But we don't have to worry about the underlying algorithms anymore. So yeah, you can find all the code on GitHub. And if you like this, please subscribe to the channel and see you next time. Bye. Hi everybody, welcome back to a new PyTorch tutorial. This time we implement linear regression. So we already implemented this step by step in the last couple of tutorials. And this should be a repetition where we can apply all the learned concepts and quickly implement our algorithm again. So as I've shown you before, our typical PyTorch pipeline consists of those 3 steps. First, we design our model. So we define the input and the output size and then the forward pass. Then we create our loss and optimizer functions. And then we do the actual training loop with the forward pass, the backward pass, and the weight updates. So let's do this. And first of all, we import a couple of things that we need. So let's import torch. Then we import torch.nn as nn, so the neural network module. Then we import NumPy as np, just to make some data transformations. And then from sklearn, we import datasets, so we want to generate a regression dataset. And then we also want to plot this later. So I say import matplotlib.pyplot as plt. And then we do our 3 steps. So we design the model, step number 1. Then step number 2, we define the loss and the optimizer. And then step number 3, our training loop. So let's do this. And first of all, let's do a step 0 where we prepare our data. So prepare data. So let's generate a regression data set. And we can do this by saying, let's call this x numpy and y numpy equals, and then we can use datasets.make regression, which gets, let's say, 100 samples. So n samples equals 100. And only one feature in this example, so n features equals 1. Then we add some noise, and let's also add a random state. Let's say this is 1. And then we want to convert this to a torch tensor. So we say x equals, and then we can use the function torch.from NumPy. And then we say x underscore NumPy, but we want to convert this to a float32 data type before. So right now this is a double data type. So if we use a double here, then we will run into some errors later. So let's just convert this by saying as type and then say numpy.float32. And we do the same thing for our y. So we say y equals the torch tensor from our NumPy array. And now let's also reshape our y, because right now this is has only one row, and we want to make it a column vector. So we want to put each value in one row, and the whole shape has only one column. So let's say y equals y.view, and here we put in the new size, so y.shape 0, so the number of values, and then only one column. So the view method is a built-in PyTorch method which will reshape our tensor. And then let's get the number of samples and the number of features by saying this is x.shape. So we can use this in a second. And now let's do our 3 steps. So now we have the data. Now we define the model. And in the linear regression case, this is just one layer. So we can use the built-in linear model. So we say model equals nn.linear. This is the linear layer, which needs a input size of our features and a output size. So let's say input size equals, this is the number of features we have. So this is just one in our example. And the output size equals 1. So we only want to have one value for each sample that we want to put in. So our model gets now the input and the output size. So input size and output size. And this is all we have to do to set up the model. And now let's continue with the loss and the optimizer. So let's call this criterion. And here we can use a built-in loss function from PyTorch, and in the case of linear regression, this is the mean squared error. So we can say this is nn.mse loss. This will calculate the mean squared error. So this is a callable function. And then we also set up the optimizer. So we say optimizer equals, and let's say torch.optim.sgd. So this is stochastic gradient descent. And our optimizer needs the parameters that it should optimize. So here we can simply say this is model.parameters. And then it needs a learning rate. So let's define this here as a variable. So let's say learning rate equals, let's say 0.01, and then LR equals learning rate. So this is step number 2. And now let's do our training loop. So first of all, let's define the number of epochs. Let's say we want to do 100 training iterations. And now for epoch in range num epochs. And now here we do our steps in the training loop, the forward pass, the backward pass, and the update and the weight updates. So let's first of all do the forward pass and also the loss here. Then the backward pass and then the update. So the forward pass and the loss, here we can say y predicted equals, and here we call our model, and as a data it gets x. So this is the forward pass, and then we compute the loss by saying loss equals, this is our we call this criterion, and this needs the actual labels and the predicted values, so y predicted and y. And now in the backward pass, to calculate the gradients, we just say loss.backward. So this will do the backpropagation and calculate the gradients for us. And then our update, here we simply say optimizer.step. So this will update the weights. And then before the next iteration, we have to be careful. So we have to empty our gradients now. Because whenever we call the backward function, this will sum up the gradients into the .grad attribute. So now we want to empty this again, and we simply say optimizer.0grad. So you should never forget this. And then we are done with the training loop. Let's also print some information. So let's say if epoch plus 1 modulo tens equals 0. So every 10th step we want to print some information. So let's print the epoch. And here we say epoch plus 1. And let's also print the loss. The loss equals, and here we can say loss.item. And let's format this. So let's plot or print only 4 decimal values. So now we are done, and now let's also plot this. So let's say, or let's get all the predicted values by saying predicted equals, here we call our final model now, model x, and with all the data. And now we want to convert this to NumPy back again. But before we do that, we want to detach our tensor. So we want to prevent this operation from being dragged in our graph, in our computational graph. Because right now, this tensor, here I have a typo, predicted. So this tensor has the required gradients argument set to true. But now we want this to be false. So this will generate a new tensor where our gradient calculation attribute is false. So this is our new tensor, and then we just call the NumPy function. Now we convert it to NumPy and now plot this. So let's say first plot all our data. So x NumPy and y NumPy. And we want to plot this as, let's say, red dots. And then we want to plot our generated or approximated functions. So let's say plt.plot x NumPy on the x-axis and our predicted labels on the y-axis. And let's plot this in blue. And then we say plt.show. And now let's run this and hope that everything is correct. And now this plot appears here. So now we see that we have a pretty good approximation of our data with this line. And we see that this is working. And yeah, now we're done. I hope you enjoyed this. If you like this, please subscribe to the channel and see you next time. Bye. Hi everybody, welcome back to a new PyTorch tutorial. This time we implement logistic regression. If you've watched the previous tutorials, then this should be very easy now. Once again, we implement our typical PyTorch pipeline with those 3 steps. So first we set up our model, we define the input and output size and the forward pass. Then we create the loss and the optimizer functions, and then we do the actual training loop with the forward pass, the backward pass, and the weight updates. The code here should be very similar to the code in the last tutorial where we implemented linear regression. We only have to make slight adjustments for the model and the loss function. So we add one more layer to our model and we select a different loss function from PyTorch's built-in functions. So let's start. First of all, let's import some things that we need. So we import torch, of course, and we import torch.nn as nn, so the neural network module. Then we import NumPy as np to make some data transformations. Then from sklearn we import datasets to load a binary classification dataset. Then from sklearn.preprocessing we want to import standard scalar because we want to scale our features. And then from sklearn.model selection we import train test split because we want to have a separation of training and testing data. And now let's do our 3 steps. So first we want to set up the model. Then we want to set up the loss and the optimizer. And then in the 3rd step we do the actual training loop. And as a step 0, we want to prepare the data. So let's do this. So let's load the breast cancer data set from sklearn. So we can say bc equals datasets.load breast cancer. This is a binary classification problem where we can predict cancer based on the input features. So let's say x and y equals bc.data and bc.target. And then we want to say, well, first of all, let's get the number of samples and the number of features by saying this is x.shape. So let's print this first. So print the number of samples and the number of features to see how our data set looks like. And we see we have 569 samples and 30 different features. So a lot of features here. And now let's continue and let's split our data when we say x train and x test and y train and y test equals, here we can use the train test split function where we put in x and y, and we want to be the test size to be 20%, so this is 0.2, and let's also give this a random state equals, let's say 1 2 3 4, and this should be a small s. And now let's convert, or first of all, now we want to scale our features, scale them. Here we set up a standard scalar, sc equals standard scalar, which will make our features to have 0 mean and unit variance. This is always recommended to do when we want to deal with a logistic regression. So now we scale our data. So we say x train equals sc.fit transform. And then as an input, we put in x train. And then we want to do the same thing with our test data. So we say x test equals sc dot, here we only transform it. And here we put in x test. Now we scaled our data. Now we want to convert it to torch tensors. So let's say x train equals torch dot, and then here we can use the function from NumPy, and then we put in x train and cast this to a float32 data type. So we say x train dot s type NumPy dot float32, because right now this is of type double, and then we would run into some errors later. So let's cast this and convert this to a tensor. And now let's do this with all the other arrays. So let's say x test equals this, and our y train, and also our y test tensor. Y test. And now as a last thing to prepare our data is to reshape our y tensors. So y train equals y train dot view. This is a built-in function from PyTorch that will reshape our tensor with the given size. So it gets the size y train dot shape 0 and 1. So right now our y has only one row, and we want to make it a column vector. So we want to put each value in one row with only one column. So this will do exactly this. And also for our y test, so y test equals this, y test. And now we are, I think we are done with our data preparing. So now let's set up our model, and here our model is a linear combination of weights and a bias. And then in the logistic regression case, we apply a sigmoid function at the end. So let's do this, and for this we want to write our own class. So let's call this model, or we can also call this logistic regression. Logistic regression. And this must be derived from nn.module. And then this will get a init, which has self, and then it gets the number of input features. And here first we call the super init. So let's say super logistic regression and self dot init. And then here we define our layer. So we only have one layer, self.linear equals, and here we can use the built-in layer nn.linear, and this gets the input size, so n input features, and the output size is just 1. So we only want to have one value, one class label at the end. And then we also have to implement the forward pass here, which has self and the data. And our forward pass is first we apply the linear layer and then the sigmoid function. So here we say y predicted equals torch.sigmoid. So this is also a built-in function that we can use. And here we apply our self.linear layer. So linear layer with our data x, and then we return our y predicted. So this is our model, and now let's create this. So model equals logistic regression of size, and here we put in the number of features that we have. So now our layer is of size 30 by 1. And no, sorry, 30 input features and 1 output feature. And now we have our model. And now we can continue with the loss and the optimizer. So for a loss, the loss function now is different than in the linear regression case. So here we say criterion equals nn.bce loss, so the binary cross entropy loss here. And our optimizer is the same. So this can be this is torch.optim.sgd for stochastic gradient descent. And this gets some parameters that we want to optimize. So here we just say model.parameters. And it also needs a learning rate. So let's say our learning rate equals 0.01, and then here we say LR equals learning rate. So now this is step 2, and now step 3. So let's define some number of epochs equals, let's say, 100 iterations, and now we do our training loop. So now we do for epoch in range num epochs, and then first we do the forward pass and the loss calculation, then we do the backward pass, and then we do the updates. So let's say y predicted equals, here we call our model, and as data it gets x train. And then we say loss equals criterion, and this will get the y predicted and the actual y training, so the training samples or the training labels. And now we do the backward pass and calculate the gradients, and again we simply have to call loss.backward, and PyTorch will do all the calculations for us. And now we update our weights. So here we simply have to say optimizer.step. And again, PyTorch will do all the update calculations for us. And then we must not forget to empty our gradients again. So want to zero the gradients, because the backward function here will always add up all the gradients into the .grad attribute. So let's empty them again before the next iteration, and we simply must say optimizer.zeroGrad, and then let's also print some information if epoch plus 1 modulo 10 equals 0. So every 10th step we want to print some information. Let's use an F string here. Let's say epoch, and here we can use epoch plus 1. And then we also want to see the loss. So the loss equals loss.item, and let's format this to say to only print 4 decimal values. And yeah, so now we are done. This is our logistic regression implementation. And now let's evaluate our model. So the evaluation should not be part of our computational graph where we want to track the history. So we want to say with torch.noGrad and then do our evaluation here. So here I want to get the accuracy. So let's get all the predicted classes from our test samples. So let's say this is model, and here we put in x test, and then let's convert this to class labels, so 0 or 1. So remember, the sigmoid function here will return a value between 0 and 1, and if this is larger than 0.5, we say this is class 1, and otherwise it's class 0. So let's say y predicted classes equals y predicted dot round. So here we can use a built-in function again, and this will do exactly this. And yeah, so if we don't use this statement, then this would be part of the computational graph, and it would track the gradient calculations for us. So here we don't want this, we don't need this because we are done. So that's why we use this with statement here. And now let's calculate the accuracy by saying ac equals y predicted classes, and here we can call the equal function equals y test, and then the sum. So we want to sum them up. For every prediction that is correct, it will add +1, and then we divide this by the number of samples, of test samples. So y test dot shape 0. This will return the number of test samples, and then let's print our accuracy. Print accuracy equals ac dot 0.4f, also only for decimal values. And now let's run this and hope that everything is correct. And standard scalar has no attribute transform. So here I have a typo. Transform. Now let's run this again. Transform. One more try. And now we are done, and we have a accuracy of 0.89. So it's okay, it's good, but it's not perfect. So you might want to play around with, for example, the number of iterations, and where do we have it? The number of epochs, or the learning rate, for example, or also maybe try out a different optimizer here. But basically, yeah, that's how we implement logistic regression. I hope you liked it. If you liked it, please subscribe to the channel, and see you next time. Bye. Hi everybody, welcome back to a new PyTorch tutorial. Today I want to show you the PyTorch Dataset and Dataloader classes. So far our code looked something like this. So we had a dataset that we loaded somehow, for example from a CSV file, and then we had our training loop that looped over the number of epochs, and then we optimized our model based on the whole dataset. So this might be very time consuming if we did gradient calculations on the whole training data. So a better way for large data sets is to divide the samples into so-called smaller batches. And then our training loop looks something like this. So we loop over the epochs again, and then we do another loop and loop over all the batches. And then we get the X and Y batch samples and do the optimization based only on those batches. So now if we use the built-in Dataset and Dataloader classes from PyTorch, then PyTorch can do the batch calculations and iterations for us. So it's very easy to use. And now I want to show you how we can use these classes. But before we jump to the code, let's quickly talk about some terms when we talk about batch training. So first, one epoch means one complete forward and backward pass of all the training samples. And the batch size is the number of training samples in one forward and one backward pass. And the number of iterations is the number of passes where each pass uses the batch size number of samples. So here we have an example. If we have 100 samples and our batch size is 20, then we have 5 iterations for one epoch, because 100 divided by 20 is 5. So yeah, that's what we should know. And now let's jump to the code. So first, I already implemented some modules that we need. So Torch, of course, then also Torch Vision. And then from torch.utils.data, we import Dataset and Dataloader, so the classes I just talked about. Then let's also import NumPy and Math. And now we can start implementing our own custom dataset. So let's call this wine dataset. And this must inherit dataset. And then we have to implement 3 things. So we have to implement the init with self. So here we do some data loading, for example. And then we also must implement the _get_item method, which gets self and an index. So this will allow for indexing later. So we can call dataset with an index 0, for example. And then we also must implement the lang method, which only has self. And then this will allow that we can call lang of our dataset. So now let's start. So in our case, we want to look at the wine dataset. So I have the CSV file here, and I also put this in my GitHub repository, so you can check that out here. And so the dataset looks like this. So the first row is the header, and here we want to calculate or to predict the wine categories. So we have 3 different wine categories, 1, 2, and 3. And the class label is in the very first column. And then all the other columns are the features. So let's load this and split our columns into X and Y. So here we can say x, y equals numpy dot load txt. And here I must specify the file name. So this is in the data folder, and then I have a wine folder, and then it's called wine.csv. Then let's also give a delimiter equals a comma here, because this is a comma separated file. Then let's also give it a data type. So let's say data type equals numpy.float32. And let's also say skip rows equals 1. So we want to skip the first row because this is our header. And now let's split our whole data set into X and Y. So we say self.x equals, and here we can use slicing, so X, Y. And we want to have all the samples, and then we don't want the very first column. So we want to start at the column number 1 and then go all the way to the end. So this will give us the X, and then self.y equals xy of. And here again, we want all the samples, but only the very first column. And we put this in another array here so that we have the size number of samples by 1. So this will make it easier later for some calculations. So yeah, and that's also convert this to a tensor. So we can say torch.from numpy, and then give this to our to the function here. So torch.from numpy. So we do not need this, but we can do it. We can also convert it later, but we can do it right here. So let's do this. And let's also get the number of samples. So let's say self.number of samples equals xy.shape and then 0. So the first dimension is the number of samples. And then we can return this right here. And this is our whole length function. So return self.number of samples. And here we can also implement this in one line. So we can say return self.x of this index and then self.y of this index. So this will return a tuple. And yeah, now we are done. So this is our data set that we just implemented. And now let's create this data set. So let's say data set equals wine data set. And now let's have a look at this data set. So now we can say first data equals data set, and now we can use indexing. So let's have a look at the very first sample. And now let's unpack this into features and labels like this. So this is first data. And now let's print the features and also print the labels to see if this is working. And yeah, so we have one feature column or only one row. So this is one row vector. And then the label, so the label 1 in this case. And yeah, so this is how we get the data set. And now let's see how we use a data loader. So we can say data loader equals the built-in data loader class. And then we say data set equals this data set. And then we can also give this a batch size. So batch size equals, let's say 4 in this case. Then let's say shuffle equals true, which is very useful for training. And this will shuffle the data. And then we also say num workers equals 2. So you don't need to do this, but this might make loading faster because it's using multiple sub-processes now. And yeah, so now let's see how we can use this data loader object. So now we can convert this to a iterator. So let's say data iter equals iter data loader. And then we can call the next function. So we can say data equals data iter dot next. And then we can again unpack this by saying features and labels equals data. And now let's print the features and the labels to see if this is working. And yeah, so here we have it. And here in this case, I specified the batch size to 4. This is why we see 4 different feature vectors here. And then also for each feature vector, the class. So 4 class labels in our labels vector or labels tensor. And now we also can iterate over the whole data loader, so and not only get the next item. So now let's do a dummy training loop. So let's specify some hyperparameters. So let's say num epochs equals 2. And then let's get the total number of samples. So total samples equals length of our data set. And now let's get the number of iterations in one epoch. So this is the total number of samples divided by the batch size. So divided by 4. And then we also have to seal this, so math seal this, and now let's print our total samples and the number of iterations. And then we see we have 178 samples and 45 iterations. So now let's do our loop. So let's say for epoch in range number of epochs. And now we do the second loop and loop over the train loader. So let's say for I, and here we can already unpack this by saying inputs and labels in enumerate, and here we only put in the, how did we call it, data loader. So this is all we have to do, and now this enumerate function will give us the index and then also the inputs and the labels here, which is already unpacked. And now what we should do typically in our training is to do our forward and then our backward pass and then update our weights. So this is just a dummy example. So in this case, I only want to print some information about our batch that we have here. So let's say if I plus 1 modulo 5 equals 0. So every fifth step we want to print some information. So let's print epoch, and here let's print the current epoch, and then all epochs. So here let's say num epochs. And then let's also print the current step. So step, and this is I plus 1. And then the total steps. So this is n iterations here. And then let's also print some information about our inputs. So inputs, and let's say here we want to print inputs.shape only. And yeah, now let's run this to see if this is working. And yeah, so here we see our print statements. So we see that we have 2 epochs, and in every epoch we have 45 steps, and every fifth step we print some information. And we also see that our tensor is 4 by 13, so we have our batch size is 4, and then 30 different features in each batch. And yeah, so that's how we use the dataset and the data loader classes, and then we can very easily get single batches. And yeah, of course PyTorch also has some already built-in data sets. So for example, from torchvision.datasets.mnist we get the famous MNIST dataset. And for example, we can also get the fashion MNIST dataset, or the Cypher dataset, or the Cocoa dataset. And yeah, so the MNIST dataset is one that we will use in one of the next tutorials. And for now, this is what I wanted to show you about the dataset and data loader classes. I hope you liked it, and please subscribe to the channel, and see you next time. Bye. Hi everybody, welcome back to a new PyTorch tutorial. This time we want to talk about transforms for our dataset. In the last tutorial we used the built-in dataset and data loader classes. And if we use a built-in dataset like we see here, then we see that we can pass the transform argument to this dataset and then apply some transforms. So in this example, we use the built-in MNIST dataset, and then we apply the to-tensor transform, which will convert imagers or NumPy arrays to tensors. And PyTorch already has a lot of transforms implemented for us. So please have a look at the official documentation, which you can find at this link. And there you can see all the available transforms. And for example, there are transforms that can be applied to images, for example, center crop or grayscale or padding. And then there are transforms that can be applied to tensors, like the linear transformation or normalize. Then there are conversion transforms, for example, the to-pillow image and the to-tensor transform. Then there are also generic transforms where we can use lambdas or we can write our very own custom class. And then we can also compose multiple transforms. So we can use transforms.compose and then pass in a list which will apply multiple transforms after each other. And yeah, so in the last tutorial we implemented a custom wine dataset. Now let's extend this class to support our transforms and write our own transform classes. So let's start. And here I copied the code from the last tutorial where we have our own custom wine dataset which will load the data. And then we implemented the getItem and the lang method, which will allow indexing and the lang function. So let's extend this dataset. So now this should also support the transform argument. So we put this in our init and say transform. Transform equals. So this is optional. So by default, this is none. And then in the init, we store this. So we say self.transform equals transform. And now we also have to make some changes to our getItem function. So here we want to apply a transform if it's available. So let's say here sample equals this. And then we say if self.transform. So if this is not none, then we apply this. So we say sample equals self.transform our sample. And then we simply return our sample. So let's return sample. And this is all the change that we need for our data set. And now let's continue and let's create some custom transform classes. For example, we can write our own to-tensor class. So in the last tutorial, we already converted it to a tensor right here in this step, but we don't need to do this. So we can leave this as a NumPy array. And then let's implement a to-tensor class, which will then be passed to our data set and which will then later convert this to a tensor. So the class to-tensor, and the only thing that we need to implement is the double underscore call method, which will get self and a sample. So now this is a callable object, and what we do here is first we unpack our sample. So we say inputs and labels or targets equals sample, and then we say return torch dot from NumPy, and here inputs, and then also torch dot from NumPy targets. So here also we still want to return a tuple like we did here. And this is all that we need for our to-tensor transform. And now we can pass this in here. So now we can say our wine data set gets the transform equals to-tensor, which is a function. And now let's have a look at this. So let's get the first item. So let's say first data equals dataset of index 0. And then let's unpack our data. So first data. So let's say features and labels equals first data. And now let's print the type of the features and also the type of the labels. So now if we run this, then we should see this is now of class torch tensor. And if we don't pass this in here, so if you say this is none, no transform, then we see that it's still a NumPy ND array. So this is how we write our own tensor, our own transform, and then apply it for our own data set. And now let's write, for example, another custom transform. So let's call this mul transform, so a multiplication. And here we implement the init method. So this has self, and this has a factor argument. So here we store this self.factor equals factor. And then again, we must implement the double underscore call function or call method, which gets self and the sample. And here again, let's unpack our sample. So let's say inputs and target equals sample. And then let's only apply the factor to our features. So let's say inputs time is multiplied by our self.factor. And now let's return our inputs, our modified inputs, and our target still as a tuple. And so this is the multiplication transform. And now let's apply this. So let's apply a, let's say, a compose transform in this case to see how we can use this. So let's say composed equals, and here we need torch vision dot transforms dot compose, and here we put in a list of our transforms. So here first we want to have to tensor, and then we want to have mul transform, and let's say, so this needs a factor, so let's say multiplied by 2. And now let's create a new data set equals wine data set, which gets the transform equals our composed transform, composed. And now again, let's get this, so let's just copy this from here and run this to see if this is working. So now here we have a tensor, and let's also have a look at the, so let's print the features, and here also print the features to see if the multiplication got applied. So here now we should see that each value got doubled. And now let's use another factor, so let's multiply it by 4 and run this, and now we should see that each of the value should now be multiplied by 4. And yeah, so this is how we can use the transform for our data sets, and it's very useful. Yeah, most of the time you see the conversion transform to tensor, but also a lot of times when we work with images, you might see some of them. So yeah, please check that out on the documentation website, and I hope you like this tutorial. Please subscribe to the channel and see you next time. Bye. Hi everybody, welcome back to a new PyTorch tutorial. This time we talk about the softmax function and the cross-entropy loss. These are one of the most common functions used in neural networks, so you should know how they work. Now I will teach you the math behind these functions and how we can use them in NumPy and in PyTorch. And at the end I will show you how a typical classification neural network with those functions look like. So let's start. And this is the formula of the softmax. So it applies the exponential function to each element and normalizes it by dividing by the sum of all these exponentials. So what it does, it basically squashes the output to be between 0 and 1. So we get probabilities. So let's have a look at an example. Let's say we have a linear layer which has 3 output values. And these values are so-called scores or logits, so they are raw values. And then we apply the softmax and get probabilities. So each value is squashed to be between 0 and 1. And the highest value here gets the highest probability. And yeah, if we sum these 3 probabilities up, then we get 1. And then this is our prediction, and then we can choose for the class with the highest probability. So yeah, that's how the softmax works. And now let's have a look at the code. So here I already implemented it in NumPy. So we can calculate this in one line. So first we have the exponential, and then we divide by the sum over all these exponentials. And now let's run this. This has the same values as in my slide. And then here we also see that the highest value, the highest logit, has the highest probability. I rounded them in my slide, so it's slightly different, but basically we see that it's correct. And of course we can also calculate it in PyTorch, and for this we create a tensor. So let's say x equals torch.tensor, and it gets the same values as this one. And then we can say output equals torch.softmax of x, and we also must specify the dimension. So we say dim equals 0, so it computes it along the first axis. And now let's print these outputs. So yeah, here we see that the result is almost the same. So this works. And now let's continue. So a lot of times the softmax function is combined with the so-called cross-entropy loss. So this measures the performance of our classification model, whose output is a probability between 0 and 1. And it can be used in multi-class problems. And the loss increases as the predicted probability diverges from the actual label. So the better our prediction, the lower is our loss. So here we have 2 examples. So here this is a good prediction, and then we have a low cross-entropy loss. And here this is a bad prediction, and then we have a high cross-entropy loss. And what we also must know is that in this case our y must be hot, one hot encoded. So let's say we have 3 possible classes, class 0, 1, and 2. And in this case, the correct label is the class 0. So here we must put a 1, and for all the other classes, we must put a 0. So this is how we do one hot encoding. And then for the predicted y, we must have probabilities. So for example, we applied the softmax here before. And yeah, so now again, let's have a look at the code, how we do this in NumPy. So we can calculate this here. So we have the sum over the actual labels times the log of the predicted labels, and then we must put a -1 at the beginning. And we can also normalize it, but we don't do this here, so we could divide it by the number of samples. And then we create our y. So as I said, this must be 1 hot encoded. So here we have other examples. So if it is class 1, then it must look like this, for example. And then down here, we put our 2 predictions. So these are now probabilities. So the first one has a good prediction because also here the class 0 has the highest probability. And the second prediction is a bad prediction. So here class 0 gets a very low probability and class 2 gets a high probability. And now then I compute the entropy, the cross entropy, and predict both of them. So let's run this. And here we see that the first prediction has a low loss and the second prediction has a high loss. And now again, let's see how we can do this in PyTorch. So for this, first we create the loss. So we say loss equals nn from the NeuroTorch nn module nn dot cross entropy loss. And now what we must know, let's have a look at the slides again. So here we have to be careful because the cross entropy loss already applies the log softmax and then the negative log likelihood loss. So we should not or must not implement the softmax layer for ourselves. So this is the first thing we must know. And the second thing is that here our y must not be 1 hot encoded. So we should only put the correct class label here. And also the y predictions has raw scores, so no softmax here. So be careful about this. And now let's see this in practice. So let's create our actual labels, and this is a torch.tensor. And now here we only put the correct class label. So let's say in this case it's class 0 and not 1 hot encoded anymore. And then we have a good prediction, y prediction good equals torch.tensor. And then here we must be careful about the size. So this has the size number of samples times the number of classes. So let's say in our case we have 1 sample and 3 possible classes. So this is an array of arrays. And here we put in 2.0, 1.0, and 0.1. And remember, these are the raw values, so we didn't apply the softmax. And here the highest, or the class 0 has the highest value, so this is a good prediction. And now let's make a bad prediction, so prediction bad. So here the very first value is a lower value, let's say, and the second value is high. And let's change this also a little bit. And now we compute our loss like this. So now we call the loss function that we created here. And then we put in the y prediction and the actual y. And the same with our second. Let's compute a second loss with y prediction bad and y. And now let's print them. So let's print L1 dot item. So it only has 1 value, so we can call the item function, and also L2 dot item. So let's run this. And yeah, here we see that our good prediction has a lower cross entropy loss, so this works. And now to get the actual predictions, we can do it like this. So let's say underscore, because we don't need this, and then predictions equals torch.max, and then here we put in the prediction, so y prediction good, and then along the first dimension, and also the same with the bad one, so let's call this prediction 1 and prediction 2. And let's print our predictions. So predictions 1 and print predictions 2. So this will, here we see that we choose the highest probability. So in this case, we choose this one. And in the second case, we choose this one. So class number 1 here. So this is how we get the predictions. And what's also very good is that the loss in PyTorch allows for multiple samples. So let's increase our samples here. So let's say we have 3 samples, so 3 possible classes. Then our tensor must have 3 class labels, our actual y. So for example, 2, 0, and 1. And then our predictions must be here of size number of samples times the number of classes. So now this is of size 3 by 3. So let's do this. So here we must put in another list with 3 values. So like this and like this. So let's say this one is a good prediction. So the first class, the first correct label is class number 2. So this one must have the highest value and this one must be low. So let's say 0.01. And here the very first one, the first class must have a high value. So like this. And then the value in the middle must have the highest raw value. So for example, like this. And then we do the same for our bad prediction. And let's say here we have this one higher. And also change this a little bit. And then we can again compute the cross entropy loss with multiple samples. And now let's run this. And then we also see here again our first prediction is good and has a low loss, and the second one is not so good. And yeah, here we get the correct predictions from the first prediction tensor. So here we also have 2, 0, 1, like in the actual y. So yeah, this is how we can use the cross entropy loss in PyTorch. And now let's go back to our slides. So now I want to show you how a typical neural network looks like. So here is a typical neural net in a multi-class classification problem. So here we want to find out what animal our image shows. So we have an input layer and then some hidden layers and maybe some activation functions in between. And then at the end we have a linear layer with one output for each class. So here we have 2 outputs. And then at the very end, we apply our softmax and get the probabilities. So now, as I said, in PyTorch, we must be careful because we use the cross entropy loss here. So we must not use the softmax layer in our neural net. So we must not implement this for ourselves. So let's have a look at how this code looks. So in a multi-class classification, our net, for example, looks like this. So we define our layers. So we have one linear layer, which gets an input size and then a hidden size. Then we have an activation function in between. And then our last layer, it gets the hidden size, and then the output size is the number of classes. So for each possible class, we have one output. And then in the forward method, so here we only apply our layers and then no softmax here at the very end. And then we create our model, and then we use the cross entropy loss, which then applies the softmax. So yeah, be careful here. And so this example also works for more classes. So if our image could, for example, also be a bird or a mouse or whatever, then this is also the correct layout. But if we just have a binary classification problem with two possible outputs, then we can change our layer like this. So now we rephrase our question. So we just say, is it a dog? Yes or no? And then here at the end, we have a linear layer with only one output. And then we do not use the softmax function, but we use the sigmoid function, which then gets a probability. And if this is higher than 0.5, then we say yes. And here in PyTorch, we use the BCE loss, or binary cross entropy loss. So here we must implement the sigmoid function at the end. So let's have a look at our neural net in a binary classification case. So again, here first we set up our layers and our activation functions. And the last layer has the output size 1. So this is always fixed in this case. And then in the forward pass, now here, after we applied our layers, we also must implement the sigmoid function. So yeah, and then here as a criterion, we use the binary cross entropy loss. So be very careful here about these two different possible neural nets. And yeah, but that's basically what I wanted to show you. So the last structure is also what I used in the logistic regression tutorial, so you can check that out if you haven't already. And for now, that's all I wanted to show you. I hope you enjoyed it and understood everything. If you have any questions, leave them in the comments below. And if you like this tutorial, then please subscribe to the channel and see you next time. Bye. Hi everybody, welcome to a new PyTorch tutorial. This time I want to talk about activation functions. Activation functions are an extremely important feature of neural networks, so let's have a look at what activation functions are, why they are used, what different types of functions there are, and how we incorporate them into our PyTorch model. So activation functions apply a linear transformation to the layer output and basically decide whether a neuron should be activated or not. So why do we use them? Why is only a linear transformation not good enough? So typically we would have a linear layer in our network that applies a linear transformation. So here it multiplies the input with some weights and maybe adds some bias and then delivers the output. And let's suppose we don't have activation functions in between. Then we would have only linear transformations after each other. So our whole network from input to output is essentially just a linear regression model. And this linear model is not suited for more complex tasks. So the conclusion is that with non-linear transformations in between, our network can learn better and perform more complex tasks. So after each layer, we typically want to apply this activation functions. So here, first we have our normal linear layer, and then we also apply this activation function. And with this, our network can learn better. And now let's talk about the most popular activation functions. So the ones I want to show you is the binary step function, the sigmoid function, the hyperbolic tangent function, the ReLU, the leaky ReLU, and the softmax. So let's start with the simple step function. So this will just output 1 if our input is greater than a threshold. So here the threshold is 0 and 0 otherwise. So this is not used in practice actually, but this should demonstrate the example of if the neuron should be activated or not. And yeah, so a more popular choice is the sigmoid function, and you should already know this if you've watched my tutorial about logistic regression. So the formula is 1 over 1 plus e to the minus x. And this will output a probability between 0 and 1. And this is typically used in the last layer of a binary classification problem. So yeah, then we have the hyperbolic tangent function, or tanh. This is basically a scaled sigmoid function and also a little bit shifted. So this will output a value between -1 and +1. And this is actually a good choice in hidden layers. So you should know about the tanh function. Then we have the ReLU function. And this is the most popular choice in most of the networks. So the ReLU function will output 0 for negative values. And it will simply output the input as output for positive values. So it is actually a linear function for values greater than 0. And it is just 0 for negative values. So it doesn't look that much different from just a linear transformation. But in fact, it is nonlinear. And it is actually the most popular choice in the networks, and it's typically a very good choice for an activation function. So the rule of thumb is if you don't know which function you should use, then just use a ReLU for hidden layers. Yeah, so this is the ReLU, very popular choice. Then we also have the leaky ReLU function. So this is a slightly modified and slightly improved version of the ReLU. So this will still just output the input for x greater than 0, but this will multiply our input with a very small value for negative numbers. So here I've written a times x for negative numbers, and this a is typically very small, so it's, for example, 0.001. And this is an improved version of the ReLU that tries to solve the so-called vanishing gradient problem. Because with a normal ReLU, our values here are 0, and this means that also the gradient later in the backpropagation is 0. And when the gradient is 0, then this means that these weights will never be updated. So these neurons won't learn anything, and we also say that these neurons are dead. And this is why sometimes you want to use the leaky ReLU function. So whenever you notice that your weights won't update during training, then try to use the leaky ReLU instead of the normal ReLU. And yeah, then as a last function, I want to show you the softmax function. And you also should already know this because I have a whole tutorial about the softmax function. So this will basically squash the inputs to be outputs between 0 and 1, so that we have a probability as an output. And this is typically a good choice in the last layer of a multi-class classification problem. So yeah, that's the different activation functions I wanted to show you. And now let's jump to the code and see how we can use them in PyTorch. So we have two options. And the first one is to create our functions as NN modules. So in our network, in the init function, first we define all the layers we want to have. So here, for example, first we have a linear layer. And then after that, we want to have a ReLU activation function. So we create our ReLU module here. And we can get that from the torch.nn module. So this contains all the different functions I just showed you. And then we have the next layer. For here example, it's a next linear layer. And then the next activation function. So here we have a sigmoid at the end. And then in the forward pass, we simply call all these functions after each other. So first we have the first linear layer, which gets an output. And then we use this output and put it into our ReLU. And then again, we use this output and put it in the next linear layer and so on. So this is the first way how we can use it. And the second way is to use these functions directly. So in the init function, we only define our linear layers, so linear 1 and linear 2. And then in the forward pass, we apply this linear layer and then also call this torch.ReLU function here and then the torch.sigmoid function directly. So this is just from the torch API. And yeah, this is a different way how we can use it. Both ways will achieve the same thing. It's just how you prefer your code. And yeah, so all the functions that I just showed you, you can get from the NN module. So here we had NN ReLU, but we can, for example, also have NN.sigmoid, and we have NN.softmax, and we have NN.tanH, and also NN.leaky ReLU. So all these functions are available here. And they are also available in the Torch API like this. So here we have torch.ReLU, then we have torch.sigmoid. We also have torch.softmax and torch.tanH. But sometimes they are not used in the functions are not available in the Torch API directly, but they are available in torch.nn.functional. So here I imported torch.nn functional as f, and then I can call here, for example, f.ReLU. So this is the same as torch.ReLU, but here, for example, is the torch is f.leaky ReLU is only available in this API. So yeah, but that's how we can use the activation functions in PyTorch, and it's actually very easy. And I hope you understood everything and now feel comfortable with activation functions. If you like this, please subscribe to the channel and see you next time. Bye. Hi everybody, welcome to a new PyTorch tutorial. Today we will implement our first multi-layer neural network that can do digit classification based on the famous MNIST dataset. In this tutorial we put all the things from the last tutorials together. So we use the data loader to load our dataset. We apply a transform to the dataset. Then we will implement our neural net with input layer, hidden layer and output layer. And we will also apply activation functions. Then we set up the loss and the optimizer and implement the training loop that can use batch training. And finally, we evaluate our model and calculate the accuracy. And additionally, we will make sure that our whole code can also run on the GPU if we have GPU support. So let's start. And first of all, we import the things we need. So we import torch. Then we import torch.nn as nn. Then we import torch vision for the data sets, and we import torch vision.transforms as transforms. And we also import matplotlib.pyplot as plt to show you some data later. And then first of all, we do the device configuration, so device config. And for this, we create a device by saying device equals torch.device. And this has the name CUDA if we have GPU support. So if torch.CUDA is available, and if it is not available, so else, we call our device simply CPU. And then later we have to push our tensors to the device. And this will guarantee that it will run on the GPU if this is supported. So yeah, so let's define some hyperparameters. And here let's define the input size. And this is 784. And this is because later we see that our images have the size 28 by 28. And then we will flatten this array to be a 1D tensor. And 28 times 28 is 784. So that's why our input size has to be 784. Then let's define a hidden size. And here I will say this is 100. You can also try out different sizes here. And the number of classes, and this has to be 10 because we have 10 different classes. So we have the digits from 0 to 9. Then let's define the number of epochs. And here I will simply say 2 so that the training doesn't take too long, but you can set this to a higher value. Then we define the batch size here, and this is, let's say, 100. And let's also define the learning rate here by saying learning rate equals 0.001. And now let's import the famous MNIST data. So you can have that from the PyTorch library by saying training dataset equals, and here we use torchvision.datasets.mnist. And this will have to have the root where it has to be stored. So root equals, and here this should be in the same folder, so dot, and then it should create a folder called data. And then we say train equals true. So this is our training data set. And then we say we apply a transform right away. So we say transform equals transforms dot to tensor. So we convert this to a tensor here. And then we also say download equals true. So it should be downloaded if it is not available already. Then let's copy this and do the same thing with our test data set. And here we have to say train equals false. And we also don't have to download this anymore. So now let's continue and create the data loaders by saying train loader equals, and here we get this from torch.utils.data.dataLoader, and then it will have to have the data set by saying dataset equals, and here it gets the training data set, so train data set. Then we have to specify the batch size, so this is equal to the batch size. And then we also have to say, or we can say shuffle equals true, so this is pretty good for training. And then we copy this again and do the same thing for our test loader. So test loader equals, it gets the test data set. And we can say shuffle equals false because it doesn't matter for the evaluation. And now let's have a look at one batch of this data by saying examples equals, and then we convert it to a iter object, iter of the train loader. And then we can call the next method and unpack this into samples and into labels by saying this equals examples.next. And now let's print the size of these. So let's print samples.shape and also print the labels.shape. And now let's save this and run this. So let's call Python feedforward.py to see if this is working so far. And yes, here we have the size of the samples. So this is 100 by 1 by 28 by 28. And this is because our batch size is 100. So we have 100 samples in our batch. Then the 1 is because we only have one channel. So we don't have any colored channels here. So only one channel. And this is our actual image array. So 28 by 28, as I said in the beginning. And our labels is only a tensor of size 100. So for each class label, we have one value here. So yeah, this is our some example data. And now let's also plot this here to see how this is looking. So for I in range 6, and here we use matplotlib. So I call plt.subplot of the with 2 rows and 3 columns and the index I plus 1. And then I can say plt.imshow. And here I want to show the actual data, so samples of I and then of 0, because we want to access the first channel. And then I will also give this a color map, so cmap equals gray. And then I say plt.show. And let's save this and run this again. And here we have a look at the data. So these are some example handwritten digits, and now we want to classify these digits. So for this we want to set up a fully connected neural network with one hidden layer. So let's do this. So let's comment this out again, and now let's create a class neural net. And this has to be derived from nn.module. And now we have to define the init and the forward method. So the init method, so this will get self. And then it will has to have the input size, then the hidden size, and then the output size. So the output size is the number of classes. And here first we want to call the super init. So super of neural net and self and dot init, self dot init. And then we create our layers. So first we want to have a linear layer by saying self.l1 equals nn.linear. And this will has the input size as input, and the output size is the hidden size. Then after the first layer, we want to apply a activation function. And here I simply use the famous ReLU activation. So self.ReLU equals nn.ReLU. And then at the end, we have another linear layer. So self.L2 equals nn.linear. And now we have to be careful. So the input size here is the hidden size, and the output size is the number of classes. And now let's define the forward method. So this will have self and one sample x. And now we apply all these layers. So we say out equals, and now we use the first layer, L1, which gets the sample x. And then the next out is self.ReLU. Now use the activation function, which will get the previous output here. And the last out equals self.L2 out. So this will apply the second linear function. And now we have to be careful again, because here at the end we don't want an activation function, so we don't apply the softmax here as usual in multi-class classification problems, because in a second we will see that we will use the cross-entropy loss, and this will apply the softmax for us. So no softmax here, so we simply say return out. So this is our whole model, and then we can create it here by saying model equals neural net. And this will get the input size, then the hidden size, and the number of classes. So yeah, now we have the model. So now let's create the loss and the optimizer. So here we say criterion equals nn.crossentropy loss. And this will apply the softmax for us. So that's why we don't want this here. So be very careful about this. And now let's create our optimizer as well by saying optimizer equals torch.optim. Now let's use the Adam optimizer here, and this has to get the parameters, and here we can use model dot parameters, and it also has to get the learning rate, LR equals learning rate. Now we have the loss and the optimizer, and now we can do our training loop. So training loop now. And for this, let's first define the number of total steps. So n total steps equals, and this is the length of the training loader. So now we can do the typical loop. So we say for epoch in range num epochs. And so this will loop over the epochs, and now we loop over all the batches. So here we say for I, and then again we unpack this. So we say images, and labels, and then we iterate over, enumerate over our train loader. So the enumerate function will give us the actual index, and then the data, and the data here is the tuple of the images and the labels. And now we have to reshape our images first, because if we have a look at this shape, then we see that this is 100 by 1 by 28 by 28, as I showed you in the beginning. And now we set our input size is 784. So our images tensor needs the size 100 by and 784 as second dimension. So the number of batches first. So let's reshape our tensor first. So we can do this by saying images equals images.reshape. And here we put in -1 as the first dimension. So then Tensor can find out this automatically for us. And here as second dimension, we want to have 28 by 28. And then we also call to device. So we will push this to the GPU if it is available. And we also have to push the labels to the device. So labels equals labels to device. And now let's do the forward pass. So first we do the forward pass and afterwards the backward pass. So the forward pass, we simply say outputs equals model, and this will get the images. And then we calculate the loss by saying loss equals, and then here we call our criterion, and this will get the predicted outputs and the actual labels. So this is the forward pass, and then in the backward pass, the first thing we want to do is call optimizer.zeroGrad to empty the values in the gradient attribute. And then we can do the next step by saying loss.backward. So this will do the backpropagation. And now we can call optimizer.step. So this will do an update step and update the parameters for us. And now let's also print print the loss. So let's say if I plus 1 modulo 100 equals 0. So every 100th step we want to print some information. So let's print the current epoch. So by saying this is epoch plus 1, and then we want to print all the epochs, so number of epochs. Then let's also print the current step by saying step, and this is I plus 1. And then the total number of steps by saying n total steps. And we also want to print the loss by saying loss equals loss.item. And let's also say we only want to print 4 decimal values. So yeah, now we are done with the training. So this is the whole training loop. And now let's do the testing and the evaluation. And for this, we don't want to compute the gradients for all the steps we do. So we want to wrap this in a with torch.noGrad statement. And then first we say the number of correct predictions equals 0 and the number of samples equals 0 in the beginning. And then we loop over all the batches in the test samples. So we say for images and labels in, and here we can simply say in test loader. And then again we have to reshape this, so like we did here. So images and labels, we want to reshape this and put it and push it to the device. And then let's calculate the predictions by saying outputs equals model. So this is our trained model now, and this will get the test images here. And then let's get the actual predictions by saying underscore and then predictions equals torch.max of the outputs and along the dimension, along the number 1. So the torch.max function will return the value and the index. So we are interested in the actual index. So this is the class label. So that's why we don't need the first actual value. So these are our predictions. And now let's say the number of samples plus equals, and here we say labels dot shape 0. So this will give us the number of samples in the current batch, so should be 100. And then we say the number of correct, so the correct predictions equals, and here we can say predictions equals the actual labels and then dot sum and then dot item. So for each correct prediction we will add +1, and then of course we have to say plus equals the number of correct values. And then when we are done with the loop, we calculate the total accuracy by saying acc equals 100 times the number of correct predictions divided by the number of samples. So this is the accuracy in %. And now let's print this. So print, and we want to print accuracy equals, and here we simply say acc. And then we are done. So now let's save this and clear this, and let's run this and hope that everything is working. So now our training starts, and we should see that the loss should be increased with every step. Sometimes it will also increase again, but finally it should get lower and lower. And now we should be done, and testing is very fast. So now we see that the accuracy is 94.9, so it worked. our first feed-forward model is done. And yeah, I hope you understood everything and you enjoyed this. If you like it, please subscribe to the channel and see you next time. Bye. Hi everybody, welcome to a new PyTorch tutorial. Today we are implementing a convolutional neural network and do image classification based on the CIFAR10 dataset. The CIFAR10 is a very popular image dataset with 10 different classes. Like we have airplanes, cars, birds, cats, and other classes. And this dataset is available directly in PyTorch, so we will create a convolutional neural net that can classify these images. So now let's talk about convolutional neural networks very briefly. I will not go into too much detail now because this tutorial should be focused on the PyTorch implementation, but I will provide further links in the description if you want to learn more in detail. So convolutional neural nets, or convnets, are similar to ordinary neural networks. They are made up of neurons that have learnable weights and biases. And the main difference now is that convolutional nets mainly work on image data and apply the so-called convolutional filters. So a typical convnet architecture looks like this. So we have our image, and then we have different convolutional layers and optional activation functions, followed by so-called pooling layers. And these layers are used to automatically learn some features from the images. And then at the end, we have one or more fully connected layers for the actual classification task. So yeah, this is a typical architecture of a CNN. And these convolutional filters, now they work by applying a filter kernel to our image. So we put the filter at the first position in our image. So this is the filter here, and this is the input image. So we put it at the first position, the red position, and then we compute the output value by multiplying and summing up all the values, and then we write the value into the output image, so here at the red position. And then we slide our filter to the next position, so the green position then, if you can see this here. And then we do the same thing and the same filter operation. And then we slide our filter over the whole image until we are done. So this is how convolutional filters work. And now with this transform, our resulting image may have a smaller size because our filter does not fit in the corners here, except if we use a technique that is called padding, but we will not cover this here in this lecture. So getting the correct size is an important step that we will see later in practice. And now let's also talk about pooling layers briefly. So pooling layers, or more specific in this case, the max pooling. Max pooling is used to downsample an image by applying a maximum filter to subregions. So here we have a filter of size 2 by 2, and then we look at the 2 by 2 subregions in our original image, and we write the maximum value of this region into the output image. So max pooling is used to reduce the computational cost by reducing the size of the image. So this reduces the number of parameters that our model has to learn. And it also helps to avoid overfitting by providing an abstracted form of the input. So yeah, these are all the concepts we must know. And again, please check out the provided links if you want to learn more. And now enough of the theory, and let's get to the code. So here I already wrote the most things that we need. So we import the things that we need. Then we make sure that we also have the GPU support. Then we define the hyperparameters. And if you don't know how I structure my PyTorch files, then please also watch the previous tutorials, because there I already explained all of these steps. So then first of all, we load the dataset. And here, as I said, the CIFAR10 dataset is already available in PyTorch, so we can use it from the PyTorch.datasets module. Then we define our PyTorch datasets and the PyTorch data loaders, so then we can do automatically batch optimization and batch training. Then I defined the classes and hard-coded them here. And then here, now we have to implement the convolutional net. And then as always, we create our model, then we create our loss and the optimizer. So in this case, as this is a multi-class classification problem, we use the cross-entropy loss. And then as optimizer, we use the stochastic gradient descent, which has to optimize the model parameters, and it gets the defined learning rate. And then we have the typical training loop, which does the batch optimization. So we loop over the number of epochs, and then we loop over the training loader, so we get all the different batches. And then here, again, we have to push the images and the labels to the device to get the GPU support. Then we do our typical forward pass and create the loss. And then we do the backward pass, where we must not forget to call to empty the gradients first here with the zero grad. Then we call the backward function and optimize a step, and then print some information. And then when we are done, we evaluate the model, and as always, we wrap this in a with torch.noGrad argument or statement. So because we don't need the backward propagation here and the gradient calculations. And then we calculate the accuracy. So we calculate the accuracy of the total network, and we calculate the accuracy for each single class. So yeah, so this is the script. You can also find this on my GitHub, so please check that out there. And now the only thing that is missing now is to implement the convolutional net. So for this, we define a class convnet, which must inherit nn.module. And as always, we have to define or implement the init function and the forward function for the forward pass. So now let's write some code here. So for this, we have a look at the architecture again. So here, first we have a convolutional layer, and then followed by a ReLU activation function. Then we apply a max pooling. Then we have a second convolutional layer with a ReLU function and a max pooling. And then we have three different fully connected layers. And then at the very end, we have the softmax and the cross-entropy. So the softmax is already included in the cross-entropy loss here. So we don't need to care about this. So yeah, so let's set up or create all these layers. So let's say self.conv1 equals, and here we get the first convolutional layer we get this by saying nn.conv2d, and now we have to specify the sizes. So the input channel size now is 3 because our images have 3 color channels. So that's why the input channel size is 3. And then let's say the output channel size is 6 and the kernel size is 5. So 5 times 5. And now let's define a pooling layer. Self pool equals nn.maxpool2d with a kernel size of 2 and a stride of 2. So this is exactly as in the image that we have seen. So our kernel size is size 2 by 2, and after each operation we shifted 2 pixels to the right. So that's why the stride is 2. And then let's define the second convolutional layer. So self-conv2 equals, and now the input channel size must be equal to the last output channel size. So here we say 6, and as output let's say 16, and kernel size is still 5. And so now we have our convolutional layers, and now let's set up the fully connected layer by saying self.fc1 equals nn.linear. And now here as an input size, so first I will write this for you. So this is 16 times 5 times 5, and as output size I will simply say 100, so you can try out a different one here. And I will explain in a second why this is 16 times 5 times 5. Then let's set up the next fully collected layer. So this has 120 input features, and let's say 84 output features. And then let's use a next or final fully connected layer. So we have FC1, FC2, and FC3. And this is an input size of 84. And the output size must be 10 because we have 10 different classes. So you can change the 120 here and also the 84. But this must be fixed, and also the 10 must be fixed. So now let's have a look at why this is this must be this number. So here I have a little script that does exactly the same thing. So let me change the number of epoch. Oh yeah, this is 4. So here I have the same thing in the beginning. I load the data set, and let's also print or plot some images. And then here I have the same layers. So here I have the first convolutional layer and the pooling layer and the second convolutional layer. And first of all, let's run this and plot the images. So let's say Python CNN test.py, and I've already downloaded it, so it prints also. Yeah, it's very blurred, but I think you can see this. This is a horse and maybe a bird and another horse, and yeah, I don't recognize this actually. So let's run this again. See some better pictures maybe. So yeah, it's still very blurred. So I think this is a deer, a car, a frog, and a ship. So yeah, so let's see how the sizes look. So first we just print images.shape. So this is 4 by 3 by 32 by 32. And this is because our batch size is 4. And then we have 3 different color channels. And then our images have the size 32 by 32. So now let's apply the first convolutional layer. So we say x equals conv1, and this will get the images. And now let's print the next size after this operation. So I don't want to plot this anymore. So now we have the next size. So this is 4 by 6 by 28 by 28. And so the 6, now we have 6 output channels as we specified here. And then the image size is 28 by 28 because, as I said, the resulting image may be smaller because our filter doesn't fit in the corners here. And the formula to calculate the output size is this. So this is the input width minus the filter size plus 2 times padding. So in this case, we don't have padding. And then divided by the stride and then plus 1. So in this example, we have an input size 5 by 5, a filter size 3 by 3, padding is 0 and stride is 1. So then we have the output size is 5 minus 3 plus 1. So this is 2. Then divided by 1 is still 2 and then plus 1. So that's why here our output image is 3 by 3. And now we have to apply the same formula in our case. So we have 32 minus the filter size, so minus 5. So this is 27 plus 0, still 27, divided by 1, still 27, and then plus 1. So that's why it's 28. So here we have 28 by 28. Then let's apply the next layer. So the next operation is the pooling layer. So let's save this and run this. So now our size is 4 by 6 by 14 by 14. So this is because, as in the example, our pooling layer with a kernel size 2 by 2 and a stride of 2 will reduce the images by a factor of 2. So yeah. And now let's apply the second convolutional layer. So let's print the size after this operation. So clear this first and run this. And then again, we would have to apply the formula as I just showed you to reduce the size. So here PyTorch can figure this out for us. So the size is 4 by 16. And this is because the next channel output size that we specified is 16. And then the resulting image is 10 by 10. And then we apply another pooling operation that will again reduce the size by a factor of 2. So this is why now we see that the final size after both convolutional layers and the pooling layers is 4 by 16 by 5 by 5. So, and now if we have a look again, so now after these convolutional layers, now when we put them into our classification layers, we want to flatten the size. So we want to flatten our 3D tensor to a 1D tensor. And now this is why now if we have a look at the size now, the input size of the first linear layer is exactly this that we have here. So 16 times 5 times 5. So this is very important to get the correct size here. But now we know why this is so. This must be 16 times 5 times 5. And now we have the correct sizes. So now we have all the layers defined, and now we have to apply them in the forward pass. So we say x equals, and now let's apply the first convolutional layer, which gets x. And then after that, we apply an activation function. So we can do this by calling f. So I imported torch and functional as f, and then I can call f.relu and then put in this as the argument. And then after the activation function, so by the way, the activation function does not change the size. So now we apply the first pooling layer, so self.pool, and wrap this here. And so this is the first convolutional and pooling layer, and then we do the same thing with the second convolutional layer. And now we have to pass it to the first fully connected layer. And for this we have to flatten it. So we can do this by saying x equals x.view. And the first size, we can simply say -1. So PyTorch then can automatically define the correct size for us. So this is the number of batches, the number of samples we have in our batch here. So 4 in this case. And then here we must say 16 times 5 times 5. And now we have our tensor flattened. And now let's call the first fully connected layer by saying x equals self.fc1. And this will get x. And then we apply an activation function. Again, we simply use the relu. I also have a whole tutorial about activation functions. So please check that out if you haven't already. So now, after this, we apply the second one. So x equals this, the second fully connected layer with a relu activation function. And at the very end, we simply have x equals self dot the last fully connected layer, fc3, with x, and no activation function at the end, and also no softmax activation function here, because this is already included in our loss that we set up here. So then we can simply return x, and this is the whole convolutional net model. Now you should know how we can set up this. And yeah, so then we create our model here, and then we continue with the training loop that I already showed you. So now let's save this and let's run this. So clear this and say python cnn.py, and hope that this will start the training. So, oh yeah, one thing I forgot, of course, is to call the super in it. So never forget to call super, and this has to get the confnet and self, and then dot underscore init. So let's clear this again and try this one more time. And now this should start the training. So I don't have GPU support on my MacBook, so this can take a few minutes. So I think I will skip this and continue when the training is done. So see you in a second. All right, so now we are back. Our training has finished, and if we have a look, we can see that the loss slowly decreased. And then we have the final evaluation. So the accuracy of the total network is 46.6%. And the accuracy of each class is listed here. So it's not very good. And this is because we only specified 4 epochs here. So you might want to try out more epochs. But yeah, now you should know how a convolutional neural net can be implemented. And I hope you enjoyed this tutorial. If you enjoyed this, please leave a like and subscribe to the channel, and see you next time. Bye. Hi everybody, welcome to a new PyTorch tutorial. In this tutorial we will talk about transfer learning and how it can be applied in PyTorch. Transfer learning is a machine learning method where a model developed for a first task is then reused as the starting point for a model on a second task. For example, we can train a model to classify birds and cats, and then use the same model, modify it only a little bit in the last layer, and then use the new model to classify bees and dogs. So it's a popular approach in deep learning that allows rapid generation of new models. And this is super important because training of a completely new model can be very time consuming. It can take multiple days or even weeks. So if you use a pre-trained model, then we typically exchange only the last layer and then do not need to train the whole model again. However, transfer learning can achieve pretty good performance results, and that's why it's so popular nowadays. So let's have a look at this picture. Here we have a typical CNN architecture that I already showed you in the last tutorial. And this, let's say this has been already trained on a lot of data, and we have the optimized weights. And now we only want to take the last fully connected layer, so this one here, and then modify it and train the last layer on our new data. So then we have a new model that has been trained and tweaked in the last layer. And yeah, this is the concept of transfer learning. And now let's have a look at a concrete example in PyTorch. So in this example, we are using the pre-trained ResNet 18 CNN. This is a network that is trained on more than 1 million images from the ImageNet database. And this network is 18 layers deep and can classify images into 1000 object categories. And now in our example, we have only 2 classes, so we only want to detect bees and ants. And yeah, so let's start. So in this session, I also want to show you 2 other new things. So first, the datasets image folder, how we can use this, and how we use a scheduler to change the learning rate. And then, of course, how transfer learning is used. So I already imported the things that we need, and now we set up the data. And the last time we used the built-in datasets from the Torch Vision datasets, and now here we use the datasets.image folder because we saved our data in a folder, and this has to have the structure like this. So we have the folder here, and then we have a training and a validation folder. So train and val. And in each one, we have folders for each class. So here we have ants and bees. And also in the validation folder, we have ants and bees. And now in each folder, we have the images here. So for example, here we have some ants. And also, let's have a look at some bees. So here we have a bee. And yeah, so you must structure your folder like this, and then you can call the datasets.image folder and give it the path, and we also give it some transforms here, and then we get the classes, the class names, by calling image datasets.classes. And then here I defined the training model where I did the loop and did the training and the evaluation. I will not go into detail here. You should already know this from the last tutorials, how a typical training and evaluation loop looks like. You can also check the whole code on GitHub, so I will provide the link in the description. So have a look at this yourself. And now let's use transfer learning. So first of all, we want to import the pre-trained model. So let's set up this model. So we can do this by saying model. So model equals, and this is available in the Torch Vision.models module. So I imported Torch Vision models already, and then I can call models.resnet16 or resnet18 here, and then I can say pre-trained equals true. So this is already the optimized weights that are trained on the ImageNet data. And now what we want to do is we want to exchange the last fully connected layer. So first of all, let's get the number of input features from the last layer. So let's say num features equals model, and we can get this by calling .fc fully connected, and then the input features. So this is the number of input features for the last layer that we need. And then let's create a new layer and assign it to the last layer. So let's say model.fc equals, and now we give it a new fully connected layer, nn.linear, and this gets the number of input features that we have. And then as new output features, number of outputs, we have 2 because we have 2 classes now. And now we send our model to the device if we have GPU support. So we created our device in the beginning as always. So this is CUDA or simply CPU. And now that we have our new model, we can again, as always, define our loss and optimizer. So we say criterion equals nn.crossentropy loss, and then let's say the optimizer equals, this is from the optimization module, optim.sgd, stochastic gradient descent, which has to optimize the model parameters. And we have to specify the learning rate equals, let's say, 0.001. And now as a new thing, let's use a scheduler. This will update the learning rate. So for this, we can create this by saying, let's call this step LR scheduler equals, and the LR scheduler is available also in the Torch optimization module. So we already imported this, and then we can say LR scheduler dot step LR, and then here we have to give it the optimizer. So here we say optimizer, and then we say step size equals 7, and then we say gamma equals let's say 0.1. This means that every 7 epochs our learning rate is multiplied by this value. So every 7 epochs our learning rate is now only updated to 10%. So yeah, this is how we use a scheduler. And then typically what we want to do is in our loop over the epoch. So for epoch in range, let's say 100. And then typically here we use the training, where we also do the optimizer.step, Then we want to evaluate it, and then we also have to call scheduler step. So this is how we use a scheduler. Please have a look at the whole loop here yourself. So yeah, now we set up the scheduler, and let's call the training function. So here we say model equals and then train model. So this is the function that I created, and then I have to pass the model, the criterion, the optimizer, the scheduler, and also the number of epochs. So num epochs, let's say 20. And yeah, so this is how we can use transfer learning. So in this case, we use a technique that is called fine-tuning, because here we train the whole model again, but only a little bit. So we fine-tune all the weights based on the new data and with the new last layer. So this is one option. And the second one is, for this I copy and paste the same thing. And let's see, where does it start? So here. And then as a second option, what we can do is we can freeze all the layers in the beginning and only train the very last layer. So for this, we have to loop over all the parameters here after we got our model. So we say for param in model dot parameters, and then we can set the requires grad attribute to false. So we can say param dot requires grad, and then say dot requires grad equals false. Now we have it, and this will freeze all the layers in the beginning, and now we set up the new last layer. We create a new layer here, and by default this requires grad equals true. And then again we set up the loss and optimizer and the scheduler in this case, and then we do the training function again. And so yeah, so this is even more faster. And let's run this and then have a look at both the evaluations, and I also print out the time that it took. So yeah, let's save this and let's run this by saying python transfer.py, and this might, first it will download all the images, and this might take a couple of seconds because I don't have GPU support here on my MacBook, so I will skip this and then I will see you in a second. Alright, so now I'm back. So this took super long on my computer, so I reset the number of epochs to just 2 in this example. So let's have a look at the results. So after only 2 epochs, so this is the first training where we did the fine-tuning of the whole model. So this took 3.5 minutes, and the best accuracy now is 0.92, so 92%. And then this is the second training where we only trained the last layer. So this took only 1.5 minutes approximately, and the accuracy is also is already over 80%. So of course it's not as good as in when we train the whole training, but still pretty good for only 2 epochs. And now let's imagine if we set the number of epochs even higher. So yeah, this is why transfer learning is so powerful, because we have a pre-trained model, and then we only fine-tune it a little bit and do a completely new task and then achieve pretty good results too. So yeah, so now I hope you understood how transfer learning can be applied in PyTorch. If you enjoyed this tutorial, please subscribe to the channel and see you next time. Bye. Hey guys, welcome to a new PyTorch tutorial. In this video we will learn how to use the Tensorboard to visualize and analyze our model and training pipeline. Tensorboard is a visualization toolkit in order to experiment with our models. It is actually developed by the TensorFlow guys, but it can be used with PyTorch as well. So here on the official website we can do a few things. We see a few things that we can do with Tensorboard. So for example, we can track and visualize metrics such as the loss and the accuracy. We can visualize our model graph. We can view histograms. We can project embeddings to a lower dimensional space, and we can display images, text and audio data, and we can profile our programs and much more. So now I want to show you how we can use this in our code. So I'm going to use the code from tutorial number 13 here. Alright, so here is the code. So this is the exact code from tutorial number 13. And if you haven't watched this one, then I recommend that you watch this one first. So I will briefly explain the code again now. So in this tutorial, we used the MNIST dataset. So we did digit classification here. So here we are loading the MNIST dataset. Then we are plotting some of the images. And then we create a simple feed-forward neural net. So this is a fully connected neural network with one hidden layer. So we see we have one linear layer first, then we have a ReLU activation function, and then another linear layer. And that's our whole forward pass. Then we set up our training pipeline. So we have our loss and optimizer. Then we do the training. So here, as always, we do a forward pass, a backward pass, and then update our weights. And then at the end, we evaluate our model and plot the accuracy. So now let's use the Tensorboard for this code to analyze our model a little bit more. And the first thing we want to do is to install Tensorboard. So for this we can do pip install Tensorboard, and this will install all the things that we need. So in my case, I've already installed this, so this was fast. And we don't have to install the whole TensorFlow library, so Tensorboard is enough here. And now we can start the Tensorboard by saying Tensorboard, and then we have to specify the path where we save the log files, and we do this by giving it the argument --logdir equals, and by default this is called in the runs directory. So let's hit enter, and then it will start up the Tensorboard at localhost 6006. And here we have a warning that it doesn't find TensorFlow, and it will run it with a reduced feature set, but that is fine. So let's open up the Tensorboard, and now here we have the Tensorboard. And right now we see that no dashboards are active, and this is because we haven't written any data. So let's do this. So let's jump to the code again. And now the first thing we want to do is to import the Tensorboard. So, and for this we say from torch.utils.tensorboard. We import, and this is called summary writer. So we import a summary writer, and so here I have a typo. And now let's create a writer. So let's say writer equals summary writer, and then let's give it a directory where it should save the log files, and the default directory is, as I said, the runs folder, but let's be more specific here. So let's call this runs and then mnist. And now we have our writer set up. And now the first thing we want to do is here. So here in the code, we plotted some images. And now instead of plotting, let's add the images to our Tensorboard. And for this, the only thing we have to do is we want to create a grid and then call the writer add image method. So let's do this. So let's say our image grid equals, and we also get this from torch_vision.utils.make grid. And then let's give it the data. So here we have one batch of our example data. So let's put this in here. And then let's call writer.addImage. And then here we give the image grid. And we also have to provide a label for this image in the beginning. So let's call this, for example, mnist images. And now I want to exit here. So I import sys, so system. And then here I use an early exit because I don't want to run the whole training pipeline right now. So here I call sys.exit, and I want to make sure that all the events are written here. So that's why I also call writer.close. So this makes sure that all the outputs are being flushed here. And now let's save this and let's go to the terminal and let's run this. So let's say Python, and then our file was feedforward.py, and hit enter. And now let's go to our Tensorboard again and let's reload this. And then we see we have our images here. And here we have our grid that we just created. And this is 8 by 8 because we specified our batch size to be 64. And yeah, so now we can analyze our data. And let's go ahead and do something more with our Tensorboard. So the next thing we want to do is to add a graph to analyze our model. So if we scroll down further, then we see that here we create our neural net. So let's comment the sys exit out again. And then here we create our model, and then here our loss and optimizer. And now down here, let's add our model graph. So we can do this by saying writer add graph. And then here we give it the model. And then we also can give it an input. So we can say, again, we have our example data. So this is one batch. And then we have to reshape the same way that we are doing it here. So let's reshape our batch data. And then again, let's call writer.close and writer exit. And system exits. And again, let's run our file. And now let's head over to our Tensorboard again and let's reload this. And then we see here up here, we also have the graphs tab. So let's go to the graph, and here we see our model. So we have the input and then the neural net. And now if we do a double click, then we see more details. So here we see our whole model. And so now we see we have the first linear layer, then we have the ReLU activation function, and then we have the second linear layer. And we also see the weights and the biases for each linear layer. So yeah, so now we can inspect this further if we want. And yeah, this is really helpful to analyze the structure of our model. So yeah, now we have our model. And now let's analyze some metrics. So what we did in the original script is we simply, during the training, we printed every 100th step, we print the current loss. So now instead of just printing this, let's add this to our Tensorboard. So let's add the training loss and also the accuracy for this. And for this, we want to have the mean loss during this batch training. So let's add two values up here before we start our loop. So the first one is our running loss. And this is 0 in the beginning. And then let's also say the running correct predictions equals 0 in the beginning. And now every 100th step we, for in each iteration now, we add the loss to the running loss. So we say running loss plus equals loss.item. And we also add the number of correct predictions to the running correct. So for this, we want to get the predictions, and we can do this the same way as we are doing it down here by calling torch.max. So let's do this up here as well. So we get the predicted values, and then we say running correct plus equals, and here we say predicted equals the actual labels, and then the sum. And this is a tensor with only one item, so we can call dot item. And now, yeah, here we add this to the running loss. And now every 100th step, we want to calculate the mean value and add this to the Tensorboard. So we call writer.addScalar. And now we have to give it a label. So here, let's give it the label training loss. And now the actual loss is the running loss divided by 100, because we sum this up for 100 steps. And then we also have to give it the current global step. And this is the by saying epoch and times the number of total steps that we extracted up here. So this is the length of the training loader, and then plus I, and I is the current batch iteration. So this is the current global step. So here we add the training loss, and now let's do the same thing again and add the accuracy. So let's say accuracy, and then here we have to say running correct divided by 100. And after that we have to set the running loss and the running predicted to the running correct to 0 again. So let's say running loss equals 0.0 and running loss, running correct equals 0 again. And then, yeah, now we have to save this, and now we have to run the whole training pipeline. So let's comment the system exit out again. And now let's run our script, and we should still see the printing outputs here. So for every 100th step, we see that how the loss is decreasing. And now we should be done. And now we also see the whole accuracy of our network. And now let's go to our Tensorboard again, and again hit reload. And then we have one more entry up here, and this is the scalars entry. And here we have our two plots. So yeah, we see that it worked. So we see the accuracy for each of the steps. And we also see how the training loss is decreasing. And yeah, so here by default, Tensorboard is smoothing this line, so we can modify the smoothing parameter here. But yeah, and now we can analyze how the loss is decreasing. And so, for example, if we see that at some point it is not decreasing further, then we can see that at this point we have to improve something. So for example, what we can do then is we can try out a different learning rate, of course. So this is usually one of the first things that we want to optimize. So let's modify the learning rate, and now let's call the folder mnist, let's say simply 2. And then again, let's clear this and run our script again. And then this should already update our Tensorboard during the file running. So now we see a second graph, and also here we see a second graph in the loss graph. Now let's reload this again, and now yeah, it should be done. And now, for example, here we see then another graph with a different learning rate. And this is how we can interactively optimize and analyze our model. And now, as a last thing, what I want to show you is how we can add a precision recall curve. So precision recall curves lets you understand your model performance under different threshold settings. And this makes more sense in a binary classification problem. But if we analyze each class separately here, then we do have a binary classification problem. So let's add a precision recall curve for each class here. And for those of you who do not know what a precision and recall mean, then I have a link for you in the description, so please check that out. And now what we want to do here is, so let's have a look at the official documentation here. So I recommend that you check out this link. So let's search for @PR, and then we see here we have the method @PR curve. So this adds a precision recall curve, and this needs the attack first, and then it needs the labels. And here we see the labels is the ground truth data, so a binary label for each element. And then it needs the predictions, and the predictions are the probability that an element be classified as true, and the value should be between 0 and 1. So this is important here. So we need to have the actual labels and also the predictions here. All right, so now let's go to the code and add a precision recall curve for each class. So here in our evaluation, we want to create a list where we store our labels. So let's say labels equals an empty list, and also a list for the predictions. So preds equals an empty list. And then during the batch evaluation, so what we do here, so for the labels, we can say labels dot append the actual labels is the predicted labels. And now for the predictions, we have to be careful. So for here, we need probabilities between 0 and 1. And now here we get the outputs from our model. And if we have a look at the neural net again, then we see that we have a linear layer at the end. So these are raw values, and here we even have a comment, so no activation and no softmax at the end, because in this case, this is applied in our loss function in the cross entropy loss. But now again, in the evaluation, we want to have actual probabilities. And if you've watched my tutorial about activation functions, then you know which activation function we must use here to get the probabilities. And this is the softmax function. So this squeezes our values to be probabilities between 0 and 1. So let's call the softmax here explicitly for our outputs. And for this, let's import f, so functional. So let's say here, let's import torch.nn.functional as f, capital F. And then down here, we want to calculate the softmax for each output in our outputs. So let's use list comprehension for this. And let's call this class predictions equals, and now here we use list comprehension and call f.softmax, and then here we say of the output. And then we do this, we also have to give it the dimension. So let's say dimension equals along dimension 0. And then we want to do this for output in outputs. And then let's add this to our, what did we call it? Preds. So preds.append, and then here class predictions. And then when we are done with the for loop, we want to convert this to a tensor. So here we say labels equals, and then torch.cut the labels. So right now this is a list, and we want to concatenate all the elements in our list along one dimension into a one-dimensional tensor. And for the predictions, we want to have a two-dimensional tensor. So for each class, we want to stack the predictions, and then we want to concatenate this. So we say preds equals, and then here we say torch.cat, and then here we use list comprehension again and say torch.stack, and here we stack each batch and say for batch in our predictions. So you should check the shape of these tensors for yourself. So this has shape, I think, how many we have? I think 10,000 samples. So this is 10,000 by 1. And this should be 10,000 by 10. So for each class, we stacked it here. And now when we are done, so now the last thing we have to do is to have the actual PR curve. So for this, we say classes. So our class labels, in this case, it's just the range 10 because we have the digits from 0 to 9. And now let's iterate over this. So for I in classes, and then we say we get the labels I equals. So this is where labels equals I. And then the same thing with the predictions I equals the predictions. And here we want to have all the samples, but only for the class I. And then we call writer dot add, and this is called add PR curve. And this needs a tag. So for the tag, we just use the class label as string. And then here we have the labels first, and then the predictions. So predictions I, and then as global step, we just use 0. And then let's call writer.close. And then we are done. So now let's save this and run our script one more time. And now when this is done, then we should see precision recall curves for each of the class labels. So almost done, and append. So I have a typo here. So I have two different labels variables. So let's call this, let's just call this labels 1 here. So labels 1 and labels 1 and labels 1. And now let's run this one more time. Sorry about that. So let's clear this and run this one more time. And now again, we have to go through the training pipeline. Oh, I didn't save it. All right, so now we are done. So let's reload our Tensorboard one more time. And now we have one more entry up here, and this is the PR curve. And now we should see the precision recall curves for each of our class labels. So here we have label 0, label 1, and so on. And then we can inspect the precision and the recall for the different thresholds. So here on the y-axis, we have the precision. And on the x-axis, we have the recall. And then, for example, for different thresholds, we can analyze it and see how many true positives, how many false positives, how many true negatives and false negatives we have. So this is also really helpful to analyze the model. And yeah, so that's all I wanted to show you for the Tensorboard. I hope you enjoyed this tutorial, and please consider subscribing to the channel, and see you next time. Bye. Hey guys, welcome to a new PyTorch tutorial. Today I want to show you how we can save and load our model. I will show you the different methods and save options you have to know, and also what you have to consider when you're using a GPU. So let's start. These are the only 3 different methods you have to remember. So we have torch.save, then torch.load, and model.loadStateDict. And these are all the methods we must remember, and I will show you all of them in detail. So torch.save here can use tensors, models, or any dictionary as parameter for saving. So you should know here that we can save any dictionary with it, and I will show you how we can use this later in our training pipeline. So torch.save then makes use of Python's pickle module to serialize the objects and saves them. So the result is serialized and not human readable. And now for saving our model, we have 2 options. The first one is the lazy method. So we just call torch.save on our model, and we also have to specify the path or the file name. And then later, when we want to load our model, we just set up our model by saying model equals torch.load and then the file name again. And then we also want to set our model to evaluation method. So by saying model.eval. So this is the lazy option, and the disadvantage of this approach is that the serialized data is bound to the specific classes and the exact directory structure that is used when the model is saved. So there is a second option, which is the recommended way of saving our model. If we just want to save our model, our trained model, and use it later for interference, then it is enough to only save the parameters. And as you should remember, we can save any dictionary with torch save. So we can save the parameters by calling torch.save and then model.stateDict. So this holds the parameters and then the path. And then later, when we want to load our model again, first we have to create the model object, and then we call model.loadStateDict, and then inside this we call torch.loadPath. So be careful here, since loadStateDict doesn't take only a path, but instead it takes the loaded dictionary here. And then again we set our model to evaluation mode. So this is the preferred way that you should remember. And now let's jump to the code to see the different saving ways in practice. So here I have a little script where I defined a small model class, and here I created our model. And now let me show you the lazy method first. So first we define our file name. So we say file equals, and let's call this model.pth. So it's common practice to use the ending .pth, so short for PyTorch. And then we save the whole model by saying torch.save and then model and the file. So let's save this and let's run the script. So let's say Python save load.py, and now if we open up our browser, so we can ignore this warning here, then we see here we have the model.pth file in the Explorer. And if we open this, then we see that this is some serialized data, so this is not human readable. And now if we go back to our code, so let's load our model. So we can comment this out, and we also can comment this out. And then we can load our model by saying model equals torch.load and then the file. And then remember, we want to set it to evaluation method. So we say model.eval, and then we can use our model. For example, we can inspect the parameters. So let's say for param in model.parameters, and then let's print our param and save this, and let's clear this and run our script again. And let me make this larger for you. So now if we run our script again, then we can see that we loaded our model and we can use the parameters. So this is the lazy option. And now let me show you the preferred way of doing this. So instead of just saying torch.save model here, what we instead want to do is to say torch.save, and then we want to save the stateDict. So here we have our model again, and then we say torch.save model.stateDict, and then let's run this. So let me clear this and let's open up the Explorer and delete this file here. And now if we run our script again, then we again have the file, but now here it only saved the state dict. And now if we want to load our model again, we first have to define it. So let's call this loaded model equals, and then let's also say the model, and the number of input features is the same, so it's 6. And then we call loaded model dot load state dict, and inside this, remember, we have to call torch dot load and then the file name. And then again we set our loaded model to evaluation mode. And then if we run this, so let's print the params of the loaded model, and up here let's also print the params of our normal model. So this, if we don't do any training here, then our model is still initialized with some random parameters. So let's run the script and let's check if the parameters are the same. So here, yeah, we see that it worked, and it first printed the parameters of the model, of the normal model, and then here of the loaded model. So these are the same. So we see we have a tensor with the weights, and we also have a tensor with the bias, and this is the same for both of our models. So we see that this worked too. So yeah, again, so this is the recommended way of doing it, by saying save.model state dict, and then when we load it, we call the load state dict method. And yeah, so here we just saved the state dict, so this holds the parameters. So let me show you how this state dict looks like. So when we have our model, let's print model.state dict, and let's save this, and let's clear this and run the script. Then we see here we have our state dict. So here we have the linear weight, which has the tensor with the weights, and then we also have the bias tensor. So this is our state dict. And now let me show you a common way of saving a whole checkpoint during training. So as you know, we can save any dictionary here. So let's say we also have a optimizer here. So let's say we defined a learning rate. So let's say this is 0.001. And we also have a optimizer. This is, let's say, torch.optim. Let's use stochastic gradient descent, and here we want to optimize the model parameters, and we also have to give it the learning rate by saying learning rate equals the learning rate. And our optimizer also has a state dict, so we can also print the optimizer state dict. Now if we clear this and run this, then we see the state dictionary of the optimizer, where we can see, for example, the learning rate and the momentum. So now during training, let's say we want to stop somewhere at some point during training and save a checkpoint. Then we can do it like this. So we create our checkpoint, and this must be a dictionary. So let's create a dictionary, and as a first thing, what we want to save is, for example, the epoch. So let's define the epoch. So the key is called epoch, and let's say we are in epoch 90. And then we want to save the model state. So we have to give it a key, let's say model state. And here we use model.stateDict. And then we also want to save the optimizer state dict. So the key, let's say optim state. And then here as a value, we have to call optimizer state dict. So this is our checkpoint. And now we can call torch.save and then save the whole checkpoint. So let's say torch checkpoint as a file name. Let's call this checkpoint.pth. And now again, let me show you the Explorer and let's run this script. So now we clear this and run this. Then we see we have our checkpoint here. And now when we load this, we want to load the whole checkpoint. So we can comment this out, and also we don't need this. So let's say our loaded checkpoint. So let's say loaded checkpoint equals torch.load. And then the file name was the same as this one. And now we have to set up the different model and optimizers again. So we can get the epoch right away by saying epoch equals loaded checkpoint. So this is a dictionary, so we can just call the or access the epoch key. And then for the model, remember we have to create our model here again. So let's say model equals, and then the model with the number of input features equals 6. And the optimizer equals the same as this one. So we don't have to use the same learning rate actually. So let me just grab this one here and paste it down here. And for example, we can use the learning rate 0, and then later we can see that we load the correct learning rate into the optimizer. So now let's say model.load state dict, and then here we give it the checkpoint, and then we access the key. We call it model state. So this will load all the parameters into our model, and the same with our optimizer. So we call optimizer dot load state dict, and then we use the checkpoint, and here we called it optim state. So now we have the loaded model and the optimizer and also the current epoch. So we can continue our training. And let me show you that this is all correct by saying we want to print the optimizer dot state dict. So if you notice here, we set the learning rate to 0, and then we loaded the correct state dict. So now if we run this, and as a last thing, we printed the optimizer state dict, then we see we have the same learning rate as in the initial optimizer. So this worked too. So this is how we can save and load a whole checkpoint. And yeah, these are all the 3 ways of saving you have to know. And now as a last thing, I want to show you what you have to consider when you are using a GPU during training. So if you are doing training and loading both on the CPU, then you don't have to make any difference. So you can just use it like I did here. But now if you save your model on the GPU and then later you want to load it on the CPU, then you have to do it this way. So let's say somewhere during your training, you set up your CUDA device and you send your model to the device and then you save it. by using the state dict. And then you want to load it to the CPU. So you have your CPU device. Then you create your model again, and then you call load state dict and then load path. And here you have to specify the map location, and here you give it the CPU device. So this is if you want to save on the GPU and load on the CPU. Now if you want to do both on the GPU, so you send your model to the CUDA device and saved it, and then you also want to load it on the GPU, then you just do it like this. So you set up your model, you load the state dict, and then you send your model to the CUDA device. And now as a third option, so let's say you saved your model on the CPU, so you didn't call model to CUDA device somewhere, but then later during loading you want to load it to the GPU. You have to do it like this. So first you specify your CUDA device, then you create your model, and then you call model.loadStateDict, and then torch load with the path, and then as map location you specify CUDA and then colon and then any GPU device number you want. So for example, CUDA colon 0. And then also you have to call model to device, so to the CUDA device. So this will send the model to the device and also all the loaded parameter tensors to the device. So then you can continue with your training or interference on the GPU. And of course, you also have to send all the training samples to the device that you then use for the forward pass. So yeah, this is what you have to consider when you're using a GPU. And now you know all the different ways of saving and loading your model. And yeah, that's all for now. I hope you enjoyed this tutorial. And if you liked this, then please consider subscribing to the channel, and see you next time. Bye.